Welcome to the RQI Circuit 2026. This is the online edition of the event. So, over the course of the past 9 weeks, we had one event in different. We had events over the local events over the RQI hubs, and now today we're here with the online edition, so that people in either smaller hubs or places that didn't explicitly apply to organize a local edition can present their work. So the first speaker today is Sergio Ernesto Aguilar Gutierrez. Hopefully I pronounced it properly. And yeah, so please, Sergio, the floor is yours.
Yeah, thanks a lot. It's nice to be to start this online circuit, this session. So this is based on work that we put up, I think, last week with these people, two from Noitz and one from Erlangen. So this is about the quantum reference frames. This is the main topic that the people in noise are interested in, at least in my group. So yeah, the point is to have like some particular type of realization of the formalism of the perspective neutral approach to quantum reference frames. So that's the point of the paper, and about the constructing a manifestly Gaussian measure for the integral that also respects some notion of so-called quantum frame covariance that we will discuss. So yeah, let me start with that. Yeah, I guess the motivation for this particular work is that we have like a several that is the potential is like a powerful tool that has several applications. Let me see. Sorry, I want to also keep. Oh no, sorry. Continue share. Yeah. Sorry, I guess I stopped the other screen. Sorry about the technical issue. Play from the start. Okay. 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 I want to keep track of the time, but I don't have the phone with me, so I hope I don't go too much over time otherwise. But okay. So yeah, the point of the paper is that we want to have yeah, like several approaches to quantum gravity. I don't know, like string theory and low quantum gravity that where the particle has like an important role. And yeah, it has like yeah, even if you want to commit yourself to a particular approach, you can also use it in general to compute the transition amplitudes, correlation functions, physical inner products, and computing, for instance, the Hartree-Hawking state or the ground state of the system you are interested in using like the clean path integral. And also for effective actions, that's for instance the approaches to asymptotic safety and so on. Or just say in normal functional renormalization group, you want to use some version of the path integral, but still there are like several problems that you would like to address. This is basically why we want to use like some relational approach. And yeah, those include about the technical or conceptual, about the, for instance, how do we do like a transition amplitudes with the time evolution included using this space and using these Euclidean path integrals or in the Lorentzian path integrals in a gravitational theory, how do we actually introduce the notion of time evolution in those cases? How do we compute like a correlation function for local space and observables or local fields? Then you need to do like some type of addressing in order to make them into something that is like a Gaussian invariant. And yeah, in that process, you might lose the locality. And also for getting like a renormalization scale in quantum gravity, what does it mean? Normally, you have to put like some cutoff that comes by hand or by some principle, but you would like to have something that doesn't break like a diff invariance. or yeah, or some notion of a renormalization scale that is particular for something that's like background independent. So you would like to use like some, I don't know, like the matter in your theory to introduce that. And there are also technical problems about like a grid of copies when you have like you don't have like some global case fixing that you can introduce. That's like in the general cases. And also about the breaking this pin bias that I also pointed out in the previous part related to reduction scale, for instance. Um, so yeah, the approach that we take in this paper is that it's like a reviving all ideas by the WIT about how to create manifestly guess invariant path integrals. Now we introduce like some new technologies with this or let's say technologies that were not accessible in the previous years when it was first introduced with this quantum reference frames. So yeah, the point of the weak construction is that you start in some field space that you will treat in a certain formalism with the principal fiber bundles. And this field space contains like a kinematical information about the field configurations. Um, and from here you can construct like some natural or like a appropriate guess invariant measure for the particle. Using like this like some type of a split between guess invariant and guess variant information. And here you can treat like some issues about the non-locality. Okay, yeah, this is basically why the width did not go further into this direction. That then there are like some things that are like less clear about the spatial locality or about the causality when you have this other type of formalism. So yeah, this is like the goal of our work, how to reconcile this with the quantum reference frame picture. So yeah, I'll try to tell you about what we do in this work. Um, sorry, I want to keep track of the time, but I have okay, I don't have a good option right now. Um, yeah, we went on like 5 minutes before that. That will be great. So thanks. Yeah, thanks. Okay. Okay. Yeah, so relational space, we have these dynamical reference frames. So this is like all well, relatively studied by people here, for instance, about the yeah, this is like some notion that we know well about the degrees of freedom that are like you can do like some get fixing or some dressing respect to matter, for instance. Then you can do like some splitting between guess redundant information and guess invariant one. So this is why we use like a reference frame in order to like get the like a relation observables that like a completely guess invariant. And then you can construct these frame fields. This is like this. Yeah, maybe at the end I will comment about some recent works related to this, but this was one of the novelties of our work, like how to introduce properly the notions of these quantum reference frames, the type of transformations in fields, in field space. Uh, so yeah, we define these frame fields as some type of field independent, I guess, covariant coordinate systems that you can use in terms of different, I don't know, certain matter degrees of freedom you have in the theory or Fermi coordinates also. So we denote by this R, and this is basically like a map that comes between a subregions in space-time, where the space-time manifold is M, and then you go to this so-called relational space that we call this matcal all respect to R, respect to a frame, and then you can define also like a subregions inside this field space. And it has like a certain properties about these frame fields. applied to like you do like some transformation where this f is like some generic function that in this case corresponds to like a diffuse in terms of this relational in terms of spacetime. Um, and this phi is just the field content that we are using. So this is what we mean by frame fields. And we have like frame transformations. So these are like we okay, there are like a different type of frame transformations. I'll describe about the frame changes and also frame orientations, and there are like two types of frame changes. So here, frame change is like a change in the description, but not the field configuration. So this is like a certain type of transformation. You can think about it in terms of passive or active transformations. So in that active case, then you have like some get invariant coordinate transformations between this R and R tilde. This is like having two reference frames. So here, this U of R to R tilde, or R prime, sorry. Yeah, it's just it's like a coordinate transformation between these two frame fields that we introduce, and this can be seen in terms of some relational observable or some observable evaluate that respect to R prime, an observable of R evaluate respect to R prime. So this is like some map between the our field space on R to R prime. And there's also this passive transformations where you yeah, by this hat, by the way, I mean that I'm using like some quotient over the symmetry group that they were interested. So I will describe about how this looks like in field space in the next slide. But here is like a specific type of coordinate transformation that are like based on this fiber bundle picture. You look like at that base space of the fiber bundle, and this is like how you want to define these passive frame transformations. There are also these frame orientations. Here you change the field configuration, but not the description. So these are like having like a diffeomorphism over the this relational space that I denote or R. So these are like a boundary symmetries or relational evolution. So in that way, you are just yeah this is indeed like a some changing the field configuration itself with respect to the frame. Uh, Okay, then we introduced this again. Okay, this was already like understood by the work by the width, but we adapted in terms of relational observables in this work. So here we denote this G as the measure in on field space, and this gamma is like it's like making a projection over the gauge orbits of the symmetry group that they were using. So this is like this G alpha B. You can like relate to this to the metric in field space where you use like a coordinate. You use like a fields that these are like some vector fields that are like related to the Lie algebra of the symmetry group that you're interested in. And yeah, this lives in a vector field space. Uh, so this X alpha that you can think about it in terms of some basis in the Lie algebra of G. And then we define like a functional integrals by doing the integration over field space with a Gaussian invariant metric with a Gaussian invariant measure. So this is a bit the technical, the like I said, definitions about how you do this functional integration that involves like some wedge products in field space with different components. These are like components in the of the field, like a coordinates in the principal fiber bundle, and here you have also like some in terms of relational observables that we define the respect. These are like the weight indices, so it has like a lot of structure inside, like all the internal internal indices and space and indices are like containing this, and also respect to these frame fields. So yeah, you can find basically that this when you compute like uh, the measure in the field space metric, that this can be like expressed in terms of like a relation observables and frame fields and other determinants that I will try to explain in the next slide. So you have also like this G bar. Yeah, thanks. Okay, that's great. So then if you have like some projection or yeah, some decomposition of the field space metric in terms of um, yeah, in terms of a horizontal part and a vertical part, and basically this G bar is like a some this is like a components respect to the horizontal part, and meanwhile the vertical part it goes like the gauge orbits. So the rest is like related to the physical to the gauge invariant part. Uh, Okay, I will not go into details, but yeah, I'm happy to take questions if there are any. And there are also like this notion of quantum frame covariance. So this is like a one improvement in our paper. Basically, we use like this splitting between gauge invariant and gauge dependent information uh, to relate like the measure in the path integral using the one that is like a gauge invariant. We can basically prove that this only depends on gauge independent information times something that is like a gauge dependent. So this epsilon hat under some redefinitions in the field space configurations. Um, and yeah, you can basically find that this measure that we computed in terms of relational observables in the base of the manifold is like a covariant on the arbitrary frame changes, and this is what we call this quantum frame covariance. So I think I have a picture about this. Perhaps I skipped this slide at some point, but this is like the picture about the I don't know, the principal fiber bundle. This is like a field space. Here you have like the configuration in terms of relational observables. These are like the coordinates or like what you can use as the natural notion of the metric in this space. And here you have like the base space of this fiber bundle. And yeah, this is basically what I mean by what we find that base space is basically what contains the gauge invariant information, and this is what you're finding for the path integral. And from there, you can find that this is like uh, this is like a covariant under frame changes. So yeah, this is like the notions of the relational path integral that we found. And yeah. At the point of this discussion is like everything expressed in terms of a single frame, but you can also like have you can do like integration where you have like a not like a globally defined coordinates along the full manifold. You need to do like a patches. You need to like compute the integration. You need to look at perform the integration over the different patches, and if there's like some overlap, you have to like take that into account to not to have like over completeness. Uh, or to subtract those parts that are like overlapping between each other. And this is using like some technology called the some atlas in like a differential geometry. We call it meta atlas in this work because you need like a different patches both in like a space and also in this relational space. And this is how basically you can do the computations of the potential in the general case where you have like a different frames that have like access to different patches in space and or in a field space. Yeah, probably I will not go into the details of the rest. I wanted to just to mention that we recall like the notions of the usual like a Fadde Popov path integrals using like a particular gauge fixing. We also found like connections to other literature based on this this manifestly gauge invariant path integral. And that they also, because of the quantum frame covariance, this also implies that there are like no gauge anomalies in the path integral. This is also like a something that is like a debate in the literature about the gauge anomalies. Uh, we also did some computations about the correlation functions. Basically, you can like find that the correlation functions of these relational observables are like gauge invariant as they should, and they are also like a quantum frame covariant, as in the notion of the particular measure that I introduced in the previous part. And yeah, something nice is that basically something that it has like a very sharp evolution. You have like events in one of the frames that like a space-time and also a field space localized. This is a field space in relational space, sorry. Then they become like a non-local in this other picture. So you have like something that is like that has like a fuzzy evolution. When you fix like a data at initial and final Cauchy slices in relational space, this is something that you find that are like a similar statements that you yeah, okay. Then I will conclude. Yeah, basically now. So you find like a similar things in the relational respective action, and yeah, also for transition amplitudes, you basically find that there is like this notion of fuzzy evolution, using like some path integral kernels that we introduced in this work. It has like this shape about the different states. Yeah, sorry that I didn't go too much into details, but those are like the main results that I just mentioned. And there are like also some notions about the Hartree-Hawking and ground states that are like a very special or very relational. So some ground state in one frame might be like an excited state in a different one. And there are like other notions that you can talk about for the no boundary proposal. So yeah, that's all. Thanks.
Great, thank you so much, Sergio. The I just don't know if we're going to have many questions coming from Zoom, because we don't have too many people here. Have most people are following through YouTube, but I do have a question. So it's I don't know if anyone else in the audience wants to ask something. Feel free, but otherwise, let me ask you. So when you're trying to basically reformulate the path integral, the gravitational path integral in terms of quantum reference frames in a more relational perspective, right? So the idea for, I mean, at least to me, the interest in quantum gravity is about trying to fix some problems that we can't really fix just by using, say, quantum field theory in curved spacetimes or things like this. And the first problem that comes to mind, for instance, is the black hole evaporation problem. Or can you use these methods to actually obtain some transitions and numbers and understand what's happening with the flow of information, say, in black holes, or in any kind of example that could really be useful to gain new results as well, apart from having the very nice formalism as well. So if you would comment a little bit on that, that would be nice.
Like at this point, it's more like we developed the formalism about what's the potential with the quantum reference frames in a perspective neutral way. But yeah, we haven't like okay, I haven't like explained you how you actually do like a practical computations, for instance, for I don't know, black hole information or other problems that the people might want to use it. Yeah, yeah, we have like some model examples in the upcoming paper where we apply to I don't know, like a simple particle cases. Yeah, in principle, the goal of this gravitational potential is to really compute something a bit beyond that, maybe include like a higher genus topologies or other type of processes that might be like relevant for the information paradox. I think that yeah, at the moment this is like some yeah long-term goal, but yeah, we don't have at the moment for some specific computation that might be more along the lines that you're asking, no, for. But yeah, that would be a goal, but we don't have it at the moment.
No, perfect. Thank you. Well, keep us informed since of the examples you apply this to. That would be nice to see for sure. Okay, so let's thank Sergio again. And I guess the next speaker, Taufiq. And you can start screen sharing too, so that we get everything ready.
Yep.
Just 1 second, the screen is loading. Okay, great. So the next speaker of today is Taufiq Murtadho, and he'll talk to us about measuring common phase in ultra-cold Bose gases. So please, Taufiq, the floor is yours.
Thank you. So yeah, thanks for this opportunity. I'm Taufiq. I'm a PhD student in NTU in Singapore. And today I'm excited to share with you our recent work on measuring common phase in Bose gases, and also some application towards detecting entanglement in quantum field simulator. So this project is a collaboration between theory group in NTU and experimental group in TU Wien, specifically the atom chip group led by Professor Jörg Schmid-Meyer. And the common phase part is published in PRR last year. You can check it out by scanning this blue QR code, while the entanglement part is just recently accepted, and you can check it out by scanning the red QR code. All right, so let me first outline the motivation and context for this project. So as you know, recently there is an unprecedented development in quantum technology, and one of the most promising applications is quantum simulation. And the idea here is you have a complex natural phenomena that's usually difficult to compute analytically or even simulate numerically, such as strongly correlated quantum materials, interacting quantum field theories, and possibly many others. And so the idea is to map this problem into some controllable quantum system in laboratories, such as ultra-cold atoms, ion trap, superconducting and photonic circuits, and also many others. And the idea is by looking into controllable system in labs, eventually we can get some insights into the complex natural phenomena of interest. For today's talk, I'm going to focus on simulating quantum field theories using ultra-cold gases. All right, so QFT. QFT is a ubiquitous framework for describing various phenomena in nature, particle physics, cosmology, critical systems in condensed matter, and many others. And oftentimes, fully solving QFT, by which I mean obtaining all correlation function, is an extremely difficult task. And so quantum field simulator can be helpful in this regard. A prominent example of interest to many people is the sine-Gordon model, which is essentially an interacting field theory where the interaction term is proportional to a cosine of the field. And this has many interesting applications, such as in torsion pendulum, in disruption junctions, in gravity, and many others. And it also has interesting topological properties, such as solitons. And in one dimension, you have some regimes where it's exactly solvable, so that if you build a quantum simulator, you know how to kind of benchmark it so that you can trust it in a more difficult regime. And in the labs, this has been simulated using different platforms, such as 1D Bose gas, spin ladder, superconducting circuits, and possibly also more. But today I will focus on tunnel-coupled 1D Bose gases as realized in the Schmid-Meyer's group in Vienna. So the way they realize this 1D Bose gas is by trapping about 10,000 bosonic atoms in anisotropic trap, strongly in two directions and weakly in one longitudinal direction, which we set to be the z-axis. And you shape the potential to have a transversal cross-section. So each 1D gas in each well is described by a bosonic field operator satisfying some canonical commutation relation. And they are well described by a macroscopic model, which is given by a tunnel-coupled Libel energy model consisting of some kinetic plus potential term, some contact interaction between the atoms, and the tunnel coupling strength, which is proportional to the rate at which the atoms in well A jump to the well B and vice versa. And realizing the effective low energy model, so at low temperature, you can decompose the field operators in terms of the phase fluctuation, which is phi, and the density fluctuation delta n, which are canonically conjugate fields. And so in order to derive some effective low energy model, you typically write down these fields in terms of the relative and common fields, which are just symmetric and anti-symmetric superpositions of the two fields. So in the end, what you get is that approximately you have decoupling between the common sector and the relative sector. And the common sector is fully described by a Tomonaga liquid model, which is quadratic in the density and the phase. But for the anti-symmetric sector, you have some tunneling term, which is proportional to the cosine of the relative phase field. And this realizes the sine-Gordon interactions. So in experiments, not only you have to be able to realize some field theory, but you also have to be able to measure them. And it's usually done by the so-called time of flight expansion, where you simply turn off the trapping potential and the two gases will expand and they will produce density interference patterns, which you can fit with a certain formula and obtain the extracted relative phase field of the two parallel 1D gas. And you can do this at different evolution times, and you can repeat the measurement many, many times. And so at each time you will have some ensemble of density interference pattern from which you can extract the relative phase and track the correlation and distribution function. And then you can learn about the system, physical information about the system, such as temperature, relaxation dynamics, non-Gaussianity, and others. All right, so in experiments, one prominent experiment is to look at the non-Gaussian statistics of this system. So one can define this n-order correlation functions, and then you take out some, let's say, the gauge degrees of freedom of the fields. And then if your field is non-Gaussian, then it can be decomposed into the disconnected part, which is decomposable via weak decomposition. And you also have the connected part, which cannot be decomposed into lower order correlation functions. And you can define the nth order non-Gaussian measure by simply taking a ratio between the connected part and the total part. This is done in 2017 in experiments. And as you can see, the y-axis is M4, which is the fourth order measure of the correlation of the non-Gaussian NITI. And the x-axis is essentially the tunneling strength. And so in the weak tunneling strength, you have more or less approximately Gaussian model, same with the strong coupling. But in the intermediate case, you have non-trivial non-Gaussianity. And in fact, they benchmark the correlation function up to the 10th order using some numerical simulations. And experimentally, you can also probe something that's more difficult to do theoretically, which is tracking how the non-Gaussianity change with time after a quench. They found that there are some regimes where you have a decay of non-Gaussianity, there are some regimes where you have recurrences, and so on. In the Gaussian case, you can get a more detailed insight into the state of the system, because for a Gaussian state, you have a one-to-one mapping to a covariance matrix. So you can extract the covariance matrix from experimental data, but note that from experimental data, you can only extract the phase. So you have to infer the elements of the covariance matrix that's related to the density fluctuation part. And this is done by quenching the system into decoupled 1D Bose gases, and then performing TOF measurement, getting the phase at different times. And this is because the evolution is such that if you express it in the eigenmode case, you have a coherent rotation between phase and density. And so you can infer the density part at t equals 0, for example, from the phase data at multiple different times. And then you can do some tomography protocol, and from the covariance matrix, you can compute various information theoretic quantities, such as entropies, mutual information, and so on. A series of experiments was done using this method. For example, in 2023, they showcased the verification of the area law of mutual information in both the Klein-Gordon case and the Sine-Gordon case. And they also track information theoretic quantities in equilibrium, out of equilibrium. However, one question that motivates me is, how do we actually detect entanglement in experiment? This is because all these experiments are not claiming anything about entanglement. And entanglement is the feature of quantum mechanics that's kind of distinguished it from classical mechanics. So you can kind of, so this is marking when your simulator is a quantum field simulator rather than just a classical field simulator. Okay, so the way I approach this problem is by looking into the measurement. So the limited available measurement, in fact, create a bottleneck to the physical phenomena that can be probed. And my research is in expanding this measurement toolbox and probe new physical phenomena. This is not only useful for experiment, but also sometimes in theory, there are some kind of like fresh lens or new insights that can be explored using this method. All right, so finally I get to the results. So in last year's paper, we seek to find ways to extract the common phase, which is just a symmetric superposition of the two-phase field. And this is done by looking into continuity equation during Toff dynamics. So if, in fact, if you look at the gas from the sides, so you cannot distinguish between gas 1 and gas 2, the common phase is encoded as a kind of center of mass velocity field of the fluids. And so if you look at one element, for example, and then after time of flight, you observe a density suppression, what happens is that there's more fluid going out rather than going in, and vice versa. And as a result, after time of flight, you'll observe a density ripple pattern from which you can extract common phase information by simply rearranging this continuity equation and solving a Poisson equation type of problem where the right-hand side is fully extractable from experimental data. So these are some numerical benchmarking. As you can see, black dash line, numerically imprinted ones, and the solid lines are the extracted ones from density ripples. Different colors are just different time of flight durations. So as you can see, essentially can recover kind of like long wavelength information, but there's still some progress to be made in reconstructing the short wavelength information, as well as taking into account the edge effects. Nevertheless, we can start computing some correlation functions. So for example, we can compute these vertex correlation functions. And let's say, because in equilibrium, this is predicted to kind of decay exponentially with distance, where the coherence length is inversely proportional to temperature. So you can start doing things like thermometry with this method. And indeed, so the y-axis here is the fitted temperature in the common sector. And this is the true temperature. So perfect reconstruction would be a straight line. And here you see that it's with this method, you're getting like accurate reconstruction of the temperature up to certain other like higher temperature where you start getting a large error bar. And you can do many other things. So for example, this 2-point function, which is important for doing tomography. You can also generalize this to higher order. And of course, for the past 20 years, there has been many like correlation function and distribution function being looked at for the relative phase. And now we can look at it for the common phase as well, such as this contrast distribution functions. And so essentially all correlation function probed before for relative phase are now accessible for the common phase. We also apply this to experimental data. So for the sake of time, I will not go into the details. But the idea here is that you can modulate the trapping potential so that only one phononic mode of the common phase is excited. And we try to implement our method. And indeed, we observed that basically one mode is excited on average for the common phase. And we kind of observe the relaxation dynamics, which essentially it just gives us a confirmation that this gives us what we expected. And so the method is kind of working quite well. We also applied it to past experimental data using tunneling quench, because the tunneling essentially happens only in the relative sector. We don't expect much to happen in the common sector, at least up to some short timescales, because in a longer timescale, you start getting a term coming from higher order, which can actually have some interaction between the relative and common sector. But indeed, up to some timescale that is probed in experiment, we see that the common vertex correlation function is essentially stationary with time. It also gives you a fresh perspective to the experimental data, because if you have the relative and common phase, you essentially have the phase of the left gas and the phase of the right gas by simply change of basis. And you can start having access toward correlation function that was not previously accessible with the previous method, such as this kind of left-right correlation and many others. And you can also extend the tomography method previously only done for the relative sector. You can also probe it for the common sector. And the interesting part is that by simply doing change of basis, you can probe the correlation between the gas A and B. And you can start looking into entanglement, mutual information, and so on. So yeah, essentially we have some numerical simulation showing how it's realistically happening in using some realistic simulation of the experimental data. So we can reconstruct the full covariance matrix up to some error coming from the phase reconstructions and the time of flight inherent error. So in terms of entanglement, what I want to talk about is that entanglement depends on the partitions. The standard way of looking into entanglement in fields is by looking into real space entanglement. So we partitioned the fields in two regions in space, for example, left and right for 1D fields. And the most famous result is, of course, the area law of entanglement, where entanglement entropy scales as area. However, this is not the only way of looking into entanglement. You can also look at momentum space entanglement of the fields. And there's another less studied, which is the field space entanglement, where we look into entanglement between two different fields, A and B. And what's interesting here is that the interaction between field A and field B can be perfectly local, but because it happens everywhere in space, the entanglement that you get is extensive. And so far as I know, field space entanglement has not been detected in experiments. So this is what I want to look at. So this is done in this paper, theoretically, I mean. So experimentally, we are still working with the experimentalists on that. But nevertheless, we look at two experimentally accessible scenarios, tunnel coupling and coherent splitting, where in coherent splitting case, you have 1D gas, and then you simply quickly quench the trapping potential into double well. And we compute logarithmic negativity and mutual information. Logarithmic negativity because we take into account the fact that we are in a finite temperature case, so that any claim about entanglement must take into account a measure that is valid for mixed state as well. We derive some explicit formula for all these quantities. I will not get into the details because the formula is quite long. However, you can check out the paper if you're interested. What's interesting is to look at the temperature needed for observing entanglement. And for example, in the tunnel coupled case, we find that mutual information only drops slightly with the temperature, but then it's almost approximately constant. Meanwhile, if you compute logarithmic negativity, it quickly drops with temperature and it basically disappears at around 3.5 nanokelvin. For context, the current experimental regime is in 30 nanokelvin. So it's one order of magnitude lower than what is realized in experiments. Nevertheless, Nevertheless, it's quite interesting because you see that because mutual information contain both quantum and classical information, meanwhile, quantum correlation decays very rapidly. So you can interpret this as a kind of, there is some kind of transmutation between quantum correlation and classical correlation. And another thing that I already mentioned is that the entanglement and mutual information scales extensively with length, but it's actually not scaling extensively with density. So this kind of underscores the fact that what's being entangled is the collective excitation of the field and not just the individual atoms. We look at the coherently splitted case. Fortunately, what we find is that in the coherently splitted case, the temperature needed to observe entanglement is much higher, and it is in the order of 36 nanokelvin in the experimental parameters. And this is reachable by the current experiment state of the art. And so this is good news, and we are currently in a close conversation with experiments in order to really detect entanglement for the coherent splitting case. Okay, so finally, I will end with some conclusion and outlook. The take-home messages is that common phase extraction in both gases is possible to be done now in experiment. It reveals new frontiers in theoretical and experimental 1D quantum field simulator by expanding the range of measurable quantities. And I mentioned some key application on detecting entanglement between excitation of multiple fields, or the field space entanglement at finite temperatures. For some future work, I would like to improve the accuracy. As I mentioned, that there's still some room to kind of recover higher short wavelength excitation of the fields, as well as the kind of like reducing noise in the kind of full tomography protocol. And finally, of course, we would like to detect entanglement in the actual experiments. And also, I'm currently in conversation with other experimentalists on monolayer and bilayer 2D Bose gases, such as realized in the Oxford. And yeah, this method is also applicable in those cases as well. And of course, entanglement is not the only application. We have in mind some other applications in studying thermalizations, non-Gaussianity, and many others. And I'm also interested to hear more. If there are ideas, you can ask me questions or also email me on the possible application of this method for studying new physics in quantum field simulator. Lastly, I would like to thank my collaborators from theory NTU side. There is Marek and Nili. And for the experimental side, there is Jörg Schmidt-Meyer, Amin Tajik, Fede, and Sebastian Erne. That's the end of my talk. Yeah, I'm around 20 minutes, so there should be time for questions. Thank you.
That's perfect. Thank you. Thank you so much for the talk. So, are there any questions from people here on Zoom? Well, if not, let me ask a couple questions. So this is all very interesting, and I personally work with entanglement quantum field theory, usually in free field theory, and just entanglement between finite regions rather than looking at area loss, but it's definitely very related, and this is super nice that you're exploring this in BCs in 1 and 2D now. My question is basically about how you would extend these results or these studies to the non-Gaussian case, which is this that you mentioned on your outlook, right?
Yes, so thank you for the question. That's a very interesting one. So here, so for the non-Gaussianity that I mentioned in the outlook, in fact, it's slightly different because the context is that in the 2D case, you have this interesting BKT physics, and not only you have phonons, you have vortices and so on. So that's what we are looking at. But in the sine-Gordon case, in fact, this is something that I'm still thinking about, because in principle, in order to talk about entanglement in the sine-Gordon full sine-Gordon case, you have to have access to the full density matrix, which is in general not experimentally accessible. So I'm currently looking into, is there a way to kind of say about entanglement, especially in mixed finite temperature case, using some correlation functions of these things. And so far, I'm still looking for like methods to do this. And if the theoretical method is there, then the next step would be to kind of, how do you do this in experiments? Would be kind of my area, translating theoretical ideas toward experiments. But yeah, so that's a very interesting question for future studies.
Okay, well, I mean, keep us updated about this. It's because most of the next talk is going to be about superposition of Gaussian processes and things like this. So it's just a superposition of Gaussian states and just non-Gaussianities in general. Studying entanglement in this case is something that I think that more and more people are becoming interested, especially in the context of field theory. So that'll be super nice. Is there any other question before we move to the next talk? I guess that if not, let's thank Taufiq again. Thank you so much for the talk.
Thank you.
Cool. So let me invite Lorenzo Braccini. You can unmute yourself and start screen sharing if you want.
Hello, everyone. Hi, Eric. Yeah, let me end the presentation in a second.
And thank you so much for accepting to deliver the talk on short notice. Don't
worry,
I think the topic fits very well too.
Can you see?
Yes, we can see the screen. Okay, great. So should I just introduce you and give you the floor? All right.
Yeah.
Okay, so the next talk is by Lorenzo Braccini, and he will be talking about superposition of Gaussian processes. So please, Lorenzo, the floor is yours.
Hello, everyone, and thank you so much for having me, Rick, and being here. Yeah, so as said from Rick, I'm going to speak about the superposition of quantum Gaussian processes, and then I will focus on entanglement sensing in a non-Gaussian limited system. I see that this is this work has been done in collaboration with my two supervisors, Sugato Bose and Alessio Serafini, and yeah, these are the two publications. I will put them at the end of the talk. And basically, this is the outline of my talk. Will be less on quantum field theory. The number of modes is finite for me, and it's more going to be oriented on the recent development in quantum optics to describe non-Gaussian state and yeah, give an analytical treatment of superposition of Gaussian processes. And basically, I start with an introduction of the motivation of why we are trying to do this. And then I will give you a very quick overview on how quantum optics and Gaussian processes has been formulated historically in the context of quantum continuous variable. And then I will try to show you the generalization that we are proposing, which tries to describe discrete variable systems like qubit and qubits entangling with the continuous variable ones. And then I will give 2 examples, and these are 2 examples of non-Gaussian matter wave interferometer that can be used to sense forces when one copy of these interferometers is considered, and then entanglement into when 2 of these copies are considered. And this is sort of try to come up with theoretical models that can give experimental prediction and insights. And this is always a work in progress. So it's this back and forth, try to discuss with the experimentalist and try to give a prediction and have feedback about it. So let's start and go directly into the motivation. And this has been a thought experiment that now people are trying to build in different laboratory around the world. And basically, the idea is that if you have a mass in a superposition of 2 positions here, left and right, and they are in a superposition with this delta x and a distance d, if you start in a product state and then you let them evolve through the Newtonian interaction, the 2 masses gets entangled. And basically, the argument goes that if gravity is classical, this will not be allowed as classical operation and classical communication and local operation cannot entangle. There is a big literature also from the RQI community about to try to describe what at the level of field theory, what this would imply. But on my side, I'm actually already spooked about this treatment. And I will also work only at the level of the Newtonian interaction. And basically, the point that happens between this initial state and this final entangled state is that what you're saying is that the state left and right of the masses are eigenstate of the position operator. And so it means that when the gravitational interaction acts on this state, given that it is also an eigenstate of this Hamiltonian. And so this leads only to the relative phases that are causing entanglement. And so, first of all, we already see that there is no kinetic term in this treatment, so we're not doing any type of dynamics. And so it doesn't describe a physical system nor an experiment. And so the problem is that if you add the classic, obviously the kinetic term, given that the momentum operator do not commute with the position ones, this is not an eigenstate anymore, and so you cannot do dynamics. Secondly, this approximation is good when the superposition is much larger than the spread of the wave function. Here I'm calling it small delta x. But the issue is that in an experiment, you don't have an initial superposition. Usually you cool up a nanoparticle or other physical system to the ground state, and then you start the dynamics to create a superposition and entangling it. And so basically, obviously, if you don't have any superposition, the requirement that the superposition is greater than the spread of the grid function. If the superposition is 0, it means that you have an infinite squeeze state, which is also consistent with the fact that we are saying that this is an eigenstate of the position operator. And so this is the second problem. And then more from an experimental point of view, this spread of the wave function is what usually encodes any noise and uncertainty in the state preparation, dynamics, and measurements of quantum states. And so if you don't treat this part of the quantum system, you lose knowledge on these topics. And basically, the question is it possible to extend the Gaussian formalism of continuous variable that allows a clear treatment of the uncertainties and the expectation values of a quantum state that is Gaussian to a superposition of Gaussian states? And basically, in the context of entanglement sensing for gravitational foundational question, on the Gaussian level, there's been an extensive analytical studies discussing how to create the localization through the squeezing of the wave function. Basically, at the beginning, it was the squeezing has been done at the level of changing the frequency trap. So by changing the frequency, like I'm plotting here, the system gets squeezed. And this has actually been recently experimentally achieved in Zurich as well in Japan. And then the second point will be to completely release the trap. And so given the free evolution of a wave packet, this will spread even faster. And then finally, where everyone is kind of trying to push is to actually create an inverted unstable potential such that the localization becomes exponentially fast. And so how we can borrow quantum information aspect of Gaussian state to describe superposition of Gaussian states, which are crucial for other type of interferometry that I will discuss later in the talk. And so let's start with a very quick overview on continuous variable and Gaussian quantum optics. This is done by this very nice book from my supervisor. Yeah, so basically, the fact that already when you have n modes, not infinite of them, the issue is that the dimension of the Hilbert space is infinite because we're working with continuous variable. And basically, you can find a very nice and compact notation by encoding the vector of observable of operators x1, p1, xn, pn in a vector, which I call R with a hat. And basically, you can write the commutational relations between the canonical observables as done here in terms of the symplectic form. And here we give an example as well as the operator. And it's remarkable how quantum optics, even though it was developed in quantum optics, has been applied to so many physical systems, such as the position and momentum of a levitated nanoparticle, because the commutator relations are quite universal. And basically, the root that how we describe those Gaussian state and systems in quantum optics is through a set of operators called the displacement operators, which displace the vacuum to a coherent state of a vector. Here I write it R bar. And basically, you can use these as a basis of operator acting on the infinite dimensional Hilbert space, and you can expand any operator in terms of this of displacement operator and a function. This function is specifically for quantum state ROS is known as a characteristic function, and this obviously fully characterized a quantum state. And for a Gaussian quantum state, indeed, this characteristic function is a Gaussian. And this is related to maybe the more famous Wigner function through a Fourier transform. And basically, the Gaussian has two parameters, a covariance matrix or second moments, which encodes the uncertainties of the state. And you can treat the coherent state, the ground state, as well as like squeeze state. And the Heisenberg relation. The relations in this form is very neat, let's say. And then you have a vector of expectation values, which tells you where the Gaussian is centered. Why do we do this? This is one example that I'm giving today is, for instance, it allows you to map a unitary or and then open and then monitor and with feedback dynamics from a Limbeladian-like equation. Here is the von Neumann one with a Gaussian Hamiltonian to the dynamics of this of the phase space. This characteristic function is the phase space representation of the quantum state, and for unitary dynamics, this is done through a symplectic transformation, which evolve, and you can write the evolution of the covariance matrix through this transformation. So we managed to map from an infinite dimensional Hilbert space problem to just few set of parameters that are the uncertainties and the expectation values of the quantum state. And basically, quantum optics is all based on this. And in a nutshell, this allows an analytical treatment of a vast number of operation measurements and dynamics that are present in laboratory. So for instance, the dynamics is mapped to time evolution of the uncertainty of the moments of the quantum state, but also measurement operation can be described as maps of those. And in general, because a Gaussian quantum state is fully characterized by these two quantities R and sigma. And the application has been done in many systems, from quantum optics, as said, to circuit quantum electrodynamic, levitated system, as well as in quantum field theory with finite number, like truncated modes. And dynamics can be done in unitary, open, continuous monitoring feedback, and measurements. Two examples of those are the homodyne and heterodyne measurement. And so basically, what I will try to outline now is that it is indeed possible to try to describe a superposition of Gaussian state in terms of a similar set of parameters and a similar set of treatment. And so one can borrow completely the whole toolbox given by quantum optics and apply it to also superposition of quantum state. And basically, I was working on two types of central Hamiltonian that are of quantum information and quantum technology. And basically, the first one is the Stenger-Luck interaction. And basically, this is a linear coupling between a qubit and a continuous variable. And this happens usually in when there is a gradient field acting on a qubit, for instance, NV centers or electrons from very early 20th century experiment up to now. And then the other one is the James coming in the dispersive regime. So basically, when you have a time-dependent resonator in the rotating wave approximation, and it's slightly off resonance compared to the frequency of oscillation of the qubit, you have this additional frequency shift induced by the presence of the qubit in the resonator. And so basically, the question is, can we write the most general Gaussian Hamiltonian of this structure and analyze it in the same way as quantum optics analyzed the Gaussian state? And so specifically, in this case, we have a general Hamiltonian that is Gaussian in the variable x and p's, and then you have only one Pauli operator that acts on the qubit. Here I write sigma z as an example, but it could be different, I think so. And basically, the answer is yes, you can do exactly as done in quantum optics. The point is that you expand first the quantum state in the basis of the qubit. And so these rho jk on the diagonal terms are Hermitian operators, but on the off-diagonal term are non-Hermitian operators. And they are non-Hermitian, anormalized, and weird, but still we can try to give a phase-space representation of this operator through displacement operators. And basically, instead of having one characteristic function for a quantum state, now in this case that I'm giving for a single qubit, there are four characteristic functions, all labeled by this classical label, which is the eigenvalue of the computational basis eigenstate of the qubit. And this we call them branched characteristic function. And then we say, okay, what is the most general Gaussian characteristic function? And this leads to the definition of a class of quite general state that is called the Gaussian cut states. And basically, as in the case before, now we have, for each characteristic function, we have the covariance matrix, the vector of first moments, and the additional two quantities, the qubit decaying contrast and qubit phases. And basically, there are sets of covariance matrix and first moments, all labeled by J and K. And in the off-diagonal terms of J and K, so J different from K, these are actually complex quantities, as in the case of this scalar part, which we can read as the qubit reduced density matrix. So if the only information that you can extract from the qubit through measurement can be done via this quantity. And basically, I will not go into the detail, but this parameterization of a Gaussian state allows us to treat any continuous variable discrete system which interacts or have operations that are conditional on the state of the system. So a superposition of Gaussian processes, let's say if the spin is up, we do a Gaussian process, and if the spin is down, we do a Gaussian processes. And this allowed us to treat unitary and open dynamics with this operator valued Hamiltonian that are like often arising in experiment. They treat n qubits n mode state We describe measurements like homodyne, heterodyne, and then CPT map and conditional operation like conditional displacements, and as we will see, and conditional rotations. And then we also develop a perturbation theory to describe also the inclusion of non-diagonal qubit terms. And now we are also working on monitoring and feedback. And basically, let's go into the detail into an example to try to build physical intuition of what this parameterization looks like and what we can learn from this state. And basically, the example that I will give that has a sort of a foundational application in gravity and quantum foundation, it's the Stagger-Luck interaction of a nanoparticle with a qubit. And so basically, if you have a nanoparticle that is trapped in a quantum harmonic oscillator and then interacts linearly with a qubit, the Hamiltonian is of this form. This has not been shown yet in an experiment, but has been predicted in several systems. The most prominent one is an NV nitrogen vacancy center in nanodiamonds, but it's also happening with the superconducting flux qubit in magnetic traps, as well as atom in optical fields in pole trap. And basically, the idea that we are doing is that we are associating, we are building a matrix of phase spaces where on the diagonal term, you have a statistical mixture of Gaussian processes. So this is like a coin cost. If you have heads, you do a Gaussian process, and if you have down, you have a Gaussian process. And so if you discard the qubit, the resulting state of the continuous variable is this statistical mixture of Gaussian state. But at the same time, this allows us to analytically treat the off-diagonal terms, where the truth part of the quantum state of a Gaussian cut state really lies. And specifically, the fact that the quantities in the phase space evolves to complex quantities. For instance, here I'm showing a conditional displacement of a Gaussian state, and as well a conditional rotation of a Gaussian state. And as you see, the R off, so the expectation value of the off-diagonal terms, evolves to complex quantities. And at the Wigner level, this means that the real part of these complex first moments is the center where the fringes are. And the complex part is the direction of where the fringes are. And this allows to build interpretation of actually what is the dynamics and what is the entanglement dynamics and what goes on. And we do also for the covariance matrix that also they evolve into to complex quantities. And then allows to give other experimental prediction and more complicated dynamics. And so the final examples that I would like to give is what happens when you consider two copies of this system that entangle through the leading order interaction that arises from gravity, but also Casimir and Coulomb. And so basically the idea is similar. We have two masses, each with a qubit. They start from a classical Gaussian state and then slowly evolves into a superposition of two Gaussians while there is a gravitational interaction between the two. And basically, this is a highly non-Gaussian Hamiltonian, but there is a procedure to move from this 4-parameter space where the force, the mass, the frequency, and the distance between the masses are the parameters accessible into experiment to a more theory-friendly parameterization by moving to unitless quantities and expanding in Gaussian order in the spread of the wave function divided by the distance. So we are just assuming that the distance between the two masses is much greater than the zero motion spread of the wave packet. And basically you reach these two quantities, which are the unitless qubit coupling. So how strongly the coupling is the coupling between the qubit and the nanoparticle, and the unitless entanglement coupling. Entanglement coupling comes through this X1, X2 interaction, which is also beam splitter, and then you have as well a frequency shift in your trap. And then on top of this, you have this operator valued force, that is the standard luck coupling, with each mass with its own qubit. And so basically, this we can treat it completely analytically. And the point is, if you look at the covariance matrix, in this case, given that the coupling is linear, there is no change between which is the qubit state and the uncertainty of your state. And so this is actually just a Gaussian dynamics with the same transformation. If it's in the unitary case, it's a symplectic transformation. And this is actually what people study when they discuss entanglement generation between a Gaussian state in the context as well of gravity. And one can, and there is this whole toolbox to how to compute entanglement correlations from the covariance matrix. And one finds that the negativity scale linearly with the time, the coupling between the two masses, and then the squeezing squared that these masses have. However, already a new insight from this treatment is the fact that the masses undergo 4 different trajectories. This is because there are 2 qubits, so there are 4 possible states that the particle can undertake. And basically, the first moment, rjk, on the diagonal term when j is equal to k, are the interferometric path that the masses take. So if you create if you use both up, both down, up, down, and down, up, the mass will have a different trajectory depending on the state, because the other mass will pull and push the other mass according to what is the qubit state and what is its trajectory. And so basically also the trajectories get entangled, and at the end of an interferometer, you will have a superposition in the Gaussian state, in the final state of the nanoparticle, and you will not be able to always recombine fully the wave packet in order to do measurement. In fact, if you, in order to do qubit measurement, you need to recombine the wave function in order to have no apparent decoherence due to a superposition somewhere. Because if some information is in the continuous variable sector, if you measure the qubit, you will lose part of the quantum information, and so your state looked decohere, while the state is with the continuous variable is also could be pure. There is a little bit issue with formatting, but basically this is a sort of a fundamental deflection that the nanoparticle undertakes, and but this is, we shall discuss, that is not a problem. Just I don't know how much time I have left. Okay, I think I can make it. Basically, through this qubit measurement, you can detect entanglement. So this will be a way to witness as well in experimental setting. And basically here I'm plotting what is the coupling, the unitless coupling on the y-axis, and the entanglement coupling G on the x-axis. So weaker is the entanglement, stronger you need the force that the mass has to experience, so you will have a larger superposition, and so once you have a larger superposition, you can measure lower couplings. The interesting point about this analysis is that if you take these 2 quantities that are the phases and the contrast is what encodes noise, and in this case specifically is the noise induced by this final superposition that the mass has, and some information has been lost from the qubit sector, and so you cannot retrieve all of it. But basically, if you do the Taylor expansion in small couplings, so you're looking at not strong coupling regimes, and you go to unitful quantities, what you find is that the phases that the mass accumulates is actually independent on the nanoparticle mass. So this is a sort of the frequency of a pendulum, which is independent on the mass. And we will go back to this point. And so basically, the question that I want to ask to conclude is, should we use atoms or LIGO mirror to make this experiment? And basically already at the unitary level, you can bound the maximum and minimum coupling that you have in order to have a negligible higher order effect, as well as to have a stable trap and don't have this fundamental deflection that takes over. And basically, these already bounce the mass to the macroscopic regime, but this is the same if you do, this becomes more stringent if you do full noise analysis. So here we discussed diffusion and the coherence, as well as imperfection in the state preparation of the nanoparticle. And basically, you can use the mass to tune such in a way that these noises are negligible. And so, I mean, this is an example with NV. We can skip. And just to conclude, this wants to be a comparison between the Gaussian regime and the non-Gaussian one. And basically, on the Gaussian regime, the superposition is within the spread of the wave function. And one finds that the entanglement rate, as I said before, is the coupling times the squeezing squared. While in the non-Gaussian regime, this is the coupling, the entanglement coupling times the entanglement coupling of the nanoparticle squared. And the fact that the mass is, the phase is independent of the mass is a direct manifestation of the Einstein equivalence principle in the Gaussian regime, because in the quantum regime, because when you create a superposition with a force, the mass enter through F equal ma, but then the interaction, the gravitational interaction as a mass squared. As you can see here, the superposition will be always inversely proportional to the mass, and so this cancels the Newtonian term. And so this is also proof of the Einstein equivalent principle in the quantum regime. And so with this, I want to conclude, and thanks to Rick for having me. I will leave this and happy to take your questions.
Thank you, Lorenzo. This is a very nice talk. I mean, it's if we had half an hour to discuss the details here, like I'm sure that we would use all of the half an hour asking questions and all this. Unfortunately, we're a little bit out of time, so I'm just going to ask you one hopefully quick question, and then hopefully we can discuss more later. So the formulas you presented at first was for when you couple any finite dimensional quantum system to a Gaussian system, right? So if you do it for all n, it seems to me that it shouldn't be too hard to push this n to infinity, which would potentially allow you to also extend these results a little bit. Have you thought about the challenges? Are you thinking about explicitly doing this? What's the...
I mean, I think there is... the point is that... so it's this parameterization of the quantum state, or this also comes through quantum optics. And basically, the point is that this will become probably an integral over all the modes. I don't know.
It doesn't have to be continuous. It doesn't have to be continuous, but it's because like if you have a discrete infinite coupling or something like this, or decomposition, in principle, it seems like most of this should work, right? And then you should be able to also just recover two Gaussian or two harmonic oscillators, or because that's O2 with discrete energy levels or something like that. But just it would be nice to think about this, I guess. But
definitely.
But surely let's discuss more later, because this is all very, very interesting, and let's get this to quantum field theory too.
So good. Happy to share everything with anyone who is interested in the community.
Amazing. Okay, thank you so much, Lorenzo. Thanks again. And yes, we're a little bit late, but that's okay. So the next speaker is Arnab, who's already ready. Hello. Do you want to screen share so that we make sure that everything is working?
I'm sharing my screen. Yes.
Okay, that's perfect. Yes, we can see it all, and we can also see your cursor, so feel free to point at things. Okay, good. So how should I pronounce your last name? Mukherjee?
Mukherjee.
Mukherjee.
Yes.
Okay. Very good. Okay, so the next speaker is Arnab Mukherjee, and he will talk to us about quantum coherence of a uniformly accelerated detector in a fermionic vacuum. So please, Arnab, the floor is yours.
Yes. Okay. So at first, I would like to thank you for giving me the chance to present my work here. So the title, as you mentioned, that quantum coherence of a uniformly accelerated detector in a fermionic vacuum. So the presentation is based on yes. So the presentation is based on this work, and this is a collaborative work between with Professor Sunandan Gangopadhyay, Dr. Pedro Barros, and Professor Helder Costa. So the outline of today's talk will be, at first I would like to give a brief overview of the motivation, and then the setup of the fermionic coupling and how it is set up there. And then we will see that what is the transition rate of the massless and massive fermionic coupling. Then I will move to the case where the accelerated quantum coherence of the accelerated qubit I will discuss, and then some discussion numerical results, and then conclude. Okay, so from the seminal work of Fulling, Davies, and Unruh, it is very well known that the particle interpretation of the vacuum is not unique. A uniformly accelerated observer in the Minkowski vacuum perceives the thermal bath of the particle, which is completely absent for the inertial observers, and the temperature of the surrounding bath is proportional to the accelerated observer. These notions are tied to the existence of a granular horizon, which is mathematically analogous to a black hole event horizon as well. So therefore, in this setup, the main key question was that how do we operationally probe this effect? And for to answer this question, it was very well known that there is a detector model, which is known as the Unruh detector model, which is a simple two-level quantum systems that couples locally to a quantum field along its world line. And with there is the ground state is usually known as referred to as the G, the excited state E, and the certain energy gap among these two levels is the omega. And there, when this detector is qubit is interacting with the field, then when there is this excitation of the detector is equivalently meaning that there is operational definition of a particle. And this kind of using this kind of detector in RQI community, it is very well known that this kind of detector is very much very used widely, and it captures the observer dependent particle content. Okay, so now the main motivation was that why do we consider the fermionic field? So main motivation behind this question that in most of the studies using these Unruh detectors are linearly coupled to the scalar field. Since fermionic fields obey different kind of statistics, so therefore it should give it is expected that the response of the fermionic field, the Unruh detector coupling with the fermionic field give a different kind of response. And for asking for regarding this kind of questions, already fermionic field has been studied in some problems and in several research directions, such as the particle detector model with fermionic field, entanglement harvesting protocol, relativistic quantum energy devices. And from the result of these studies shows some importance of the fermionic field. So therefore, we find that what will be the effect of quantum coherence if we consider the detector couples to a fermionic spinor field, and specifically if the field has a mass term. So that's why we are in this work we compute transition rates for massless and massive fermionic coupling and use them to track the quantum coherence of an accelerated qubit. So when the detector couples to the fermionic spinor field through the monopole moment, the interaction Hamiltonian is looking like this way, where the lambda is the coupling strength, and the chi tau is the switching function. In this case, we consider the Gaussian switching function. And here also there is a normal ordering is required there because fermionic coupling has a persistent divergences, which is not curable by using the switching or smelling function. So that's why we need the normal ordering. Now, when we evolve these kind of, when we see the time evolution using this kind of interaction Hamiltonian and then trace out the field degrees of freedom, then finally up to first order of these first order interaction, and then we consider we get the transition probability will be looking like this, and the response function will be looking like this. where these P minus is the acceleration probability and the P plus is the re-acceleration probability, and the x and the x prime are the detector's trajectory at different proper times, tau and tau prime. Now, if we expand the switching function in a Taylor series around tau equals to 0, the response function becomes this kind of structure, where these f infinity is the response function for the scenario where if we let the detector interact with the field for an infinite time. And similar kind of similar kind of expression we also had for these the transition probability per unit time. So here also we found that these R infinity is also the transition probability per unit time for the scenario when the detector is interacting with the field for an infinite time there. And if the leading of the transition probability rate transition probability rate can be expressed in these way. So therefore, the second term can be considered as some kind of corrections to the transition probability per unit time for the infinite time there. And this R minus is the rate of acceleration probability, R plus is the rate of the re-acceleration probability. Now to compute this transition probability per unit time, we need the Weidmann function. So here at first we will go for the massless harmonic Weidmann function. So therefore, for calculating the massless harmonic Weidmann function, we need to the massless scalar Weidmann function, and using this kind of formula, we can calculate the massless harmonic Weidmann function. So it is very well known that massless scalar Weidmann function takes this kind of structure, where with the observer's coordinate, and for the trajectory of the uniformly accelerated observer is looking like this, and if we plug this trajectory in this function, then it looks like this kind of structure. And using this massless scalar Weidmann function, if we plug it in this formula, then we get the massless harmonic Weidmann function there. Now, after calculating the transition rate for the massless case, we find that infinite time transition rate will be looking like this, where if we look carefully, then we found that this omega by this factor with a 1 by 2 pi previous factor it is the infinite transition rate for the scalar field. So when we calculate the fermionic field, we found that there are some kind of additional acceleration additional term is there, which is proportional to the acceleration. So this is the excitation probability, and we already know that if we multiply the e to the power 2 pi into omega by a, this kind of factor with the acceleration probability, we get the de-acceleration probability, and this comes from the principle of detail balance. So now when we calculate the finite time transition rate, we find that this is a huge structure, and there is a bar is and the sigma are the dimensional parameter, and here we are using the natural unit system. So therefore the a by omega and the omega t are the dimensional parameters. So here all these from the second term, the other rest of the terms are associated with these parameters. So when we take lambda tends to infinity, such a which means that we are taking with the infinite interaction. So therefore, all these terms will be dropped out, and then this result is coincide with this result. Now, when we add a mass term there, so for a massive fermionic field, the main formula for calculating the Weidmann function is looking like this. And here we need to, for calculating the massive fermionic field Weidmann function, we need the massive scalar field Weidmann function. And using the form of the massive scalar field Weidmann function and incorporating the trajectory of the uniform accelerator, we finally get this kind of structure, where this K1 and the K2 are the modified Bessel functions. And since this the structure of the massive harmonic Weidmann function is a bit heavy. So therefore, here we consider two limiting case for the rest of the studies. So one is this m by a ratio less than 1, and the m by a ratio is greater than 1. So for these n by a ratio less than 1, we call this regime as the small mass regime, and the other regime is the large mass regime. Now, when we calculate the transition rate for the small mass regime, we get this kind of structure, and as well as for finite time acceleration rates also we get this kind of structure. From there, we can see that if we put this m bar, which is the ratio m by omega, which is the energy gap of the energy level of the qubits to energy level. So when we put m bar tends to 0 limit, then we found that this result is going to back to the massless scenario. And for that, from this analytical structure, we can find that mass enters as a small negative correction, and the response is a bit, and the detector is slightly less responsive than the massless one, since this is the response of the massless scenario. So therefore, this massless scenario minus some term. So therefore, this is less than this one. Now, when we see the large mass regime, so for the large mass regime, we get the infinite acceleration rate in this way. And here we can see that the entire term is mass dominated, and the finite time acceleration rate is also mass dominated. And when we see put the limit m bar tends to infinity, we found that this result is basically mathematically gives us negative value. But since this is a transition rate, so therefore from physical argument we can argue that a transition rate cannot be negative. So therefore it forces the transition rate tends to 0. So which indicates that for heavy particles are increasingly hard to absorb. And since the large mass limit has the transition rate tends to 0, so therefore for the subsequent analysis we will consider only the small mass regime there. Now, if we vary the small mass transition rate with respect to the acceleration as well as the mass term, then we found that when we increase the acceleration, then initially the transition rate is very low, and after a certain value, it just spikes up there. And for a particular acceleration value, if we change the mass term, the value of mass, then we found that for the highest mass value, the transition rate is the lowest. And similarly, if we vary taking the variation with the mass term, then we also found that when we increase the mass term there, therefore transition rate decreases. And for a fixed mass term, if we increase the acceleration, then we found that transition rate increases there. So therefore, for both the figures are consistent with each other. Now we will see that what will be the quantum coherence of the accelerated qubit scenario. So for this scenario, initially we started with the qubit state, which is a superposed state. So there alpha is the e to the power I5 by 2 cos theta by 2, beta equals to the power I5 by 2 minus I5 by 2 sin theta by 2, and the theta range is the 0 to pi, and the phi is the 0 to 2 pi in the Bloch scale. So here also we consider the Minkowski vacuum, and after the time evolution and tracing out the field, we found the reduced density matrix in this kind of form. So here we have to notice that initially when we have considered the detector is starting with its ground state, for that scenario we usually get only the diagonal term. Off diagonal term remains 0 there. But since here we consider that qubit is starting with a superposed state, so therefore we found that the off diagonal term is also there present. And since off diagonal is present there, so therefore we can calculate the L1 norm of coherence, which is the sum of off diagonal terms. So therefore, and for evaluating the coherence, we are considering the long interaction time, the sigma greater than 1 value. So when we calculate the coherence term for the massless scenario, we get this kind of structure, which depends on this coupling constant, and this is the second leading order of the coupling constant, and the lambda square. And this depends on the acceleration and this coupling constant there. So therefore, and since this term is 1 minus this term, so therefore when we increase this acceleration as well as coupling constant there, So coherent decays monotonically. And for the massive case, we also find a similar kind of structure, but there is a important catch is that there is a mass term is there, and since mass term is there, so therefore for this case, if we change the acceleration as well as mass term, so therefore we cannot say that it is always monotonically degrade, which was the case for the massless scenario. So, and in this case, if we put m equals to 0, then it gets to get back to the previous result. And so therefore, if we take the variation of the acceleration and this coupling constant, then we found that for increasing, as we see from the analytical result, that increasing both acceleration and coupling constant degrades the coherence more rapidly. Now, if we consider the fermionic coupling versus scalar coupling and plot these coherence for both the scenario, then we found that for the scalar coupling scenario, when we increase the acceleration, the coherence is more or less similar, more or less remains at the same level. But after a certain value of acceleration, fermionic field rapidly degrades. So this suggests that fermionic coupling produces a stronger detector response than the scalar one. And this is the reason that it degrades much faster than the scalar coherence at equal coupling scale. And another thing is that fermionic detector in d dimension is equivalent to scalar detector in 2D dimensions. So therefore, fermionic detector has some richer phase space and more interaction channels, so that it degrades much faster with respect to the scalar field. Now, when we take the behavior of the show the behavior of the massive coherence with respect to the acceleration and the mass term, so then we found an interesting result. So here we consider when we see the increase the acceleration for a fixed value of mass term, we found that it is degrading, which is very equivalent, which is similar structure as the massless scenario. But for a particular acceleration, if we increase the mass term, so then we can find that coherence is increasing there. So this is an important result for this massive field. And similarly for this scenario also, we found that when you increase the mass term there, so therefore the coherence is increasing. So therefore mass acts as a protective factor against these Unruh-induced decoherence. So this is an important result for the perspective of the relativistic quantum information fraternity, because these kind of controlling the coherence is a bit challenging. So therefore, if we consider you take this kind of massive coupling, coupling with a massive field, so therefore there is a chance that mass itself has a protective measure against this kind of decoherence. So now I will conclude that. So therefore, in this work, we derive the transition probability rates for a Unruh detector coupled to the massless as well as massive fermionic spinor fields. And we found that fermionic coupling produces a stronger detector response than the scalar coupling, which is the faster coherence degradation there. The particle mass suppresses the transition rate and thereby mitigates the coherence loss. And the implication for the RQI is the field mass is a lever to control information loss in accelerated quantum systems. So thank you.
Thank you so much, Arnab. Are there any questions? I see that Mike Good is here, so probably.
Yeah, thank you, Arnab. A very nice talk. I really liked it.
Thank you.
A quick question is if you, during your exploration of the mass, did you find that it could act as a lever to change any of the statistical formality? I mean, I know, of course, you're saying this it affects the coherence and decoherence, but did you check out whether it changes some equilibrium or has any effect on the statistics, like in that sense?
No, I haven't checked that portions.
So you probably.
I will
assume it's still in equilibrium, even with it's a massive field, still that nice Planck distribution. Is that what you would say is safe? Okay, thank you.
Thank you for the question.
Yeah.
Good, and let me ask you something too, Arnab. So everything that you've considered so far was, if I understand correctly, for one detector interacting with this fermionic field with the quadratic coupling, right? So there are a couple of results from other fields as well, and also that study entanglement harvesting from, say, scalar field with 2 accelerated detectors on the 2 wedges, right? And if I understand correctly, it's possible to establish some sort of trade-off between coherence of this 2 detector states and the entanglement that they can acquire and things like that. So it's I'm just saying that it would be very nice to have this study done for 2 detectors and to see how entanglement and coherence play a role up to some extent, and you can increase one by decreasing the other and vice versa. So that might be nice. And the other thing is that it's also possible to consider linearly coupled detectors to fermionic fields. It's just that your detector then has to have a fermionic degree of freedom that couples to the fermionic field, right? And then you wouldn't have to need...
linearly coupled means only with psi.
Yes, so basically your detector would have to have a fermionic, if you want, degree of freedom, or a fermionic, like, you need a fermionic smearing function, if you will. And then this is going to be contracted with your fermionic field. And this linearly coupled case is just, it's slightly different, but it might be actually harder, easier to handle than the quadratically coupled, because in this case, everything will be regular on the response and all these things. So it might be a good idea to look at these things. And also,
yes,
I mean, it's this linear coupling might be interesting in the sense that this is how nucleons in atoms couple to, say, the neutrino field, right? It's, the nucleon itself has effectively a fermionic degree of freedom, it couples there, and you can relate this with the 4 fermion interaction and all this. So just saying that this might also be an interesting follow-up direction for you to...
Thanks for these suggestions. I will see that. Okay.
Good, perfect. So if there are no further questions, let's thank Arnab again. And although Zoom really prevents the clapping sounds, so people can't really hear it on Zoom, but okay, cool. So the next speakers should be Nitesh Dubey.
Yeah, thanks. So can I share?
Perfect. Okay. So feel free to start screen sharing, and yep.
Yeah, I have. So perhaps you can see my screen.
Just give us 1 second. I think it's loading, but we will be able to see it shortly. I presume. So it's still, we're still waiting for it. Okay, there we go. We can see it, and we can see your cursor too. So that's good. So Michael, let me just ask you to switch off your camera, because otherwise you're gonna... Yeah, okay, that's perfect. Okay, and Nitesh, if you want to switch on your camera, feel free, but if you don't, it's also perfectly fine. Cool, so let me introduce you, and let's start the next talk, I guess. So the next talk is by Nitesh Dubey, and they'll talk about memory effects and entanglement dynamics of finite time acceleration. So please, the floor is yours.
Yeah, thanks, Nick, for kind introduction and giving me opportunity to present. I'll be talking about memory effects and entanglement dynamics of an unreliable detector based on a finite duration accelerated trajectory. So based on this paper. So first I will introduce the trajectory and its focus-based relation with the inertial frame focus-based. Then we'll put one unreliable detector along this trajectory, see its response rate and memory effects. Then we take 2 such detectors and study entanglement harvesting using them. So we know in relativity, time depends on choice of observer, reference frame. As a result, different observers can have different notions of frequency, positive and negative frequencies. As a result, concept of particles, which are excitations of fields in momentum space, they are also different for different observers. And in this regards, first major results came due to this Unruh and Davis, where this Davis could say that the result is that an observer who undergoes a uniform acceleration kappa apparently sees a fixed surface radiate at temperature kappa by 2 pi. So just 1 second. Yeah. So after this results of Unruh and Davis, people did this calculations for different scenario and different methods. is like, for example, for the case of black holes, though it came earlier, we can associate this Hawking temperature with black holes, and this kind of de Sitter temperature with de Sitter horizon. One motivation behind studying this linearly uniformly accelerating trajectory in Minkowski spacetime is that like near horizon geometry of the non-extremal black hole can be written like this, which is a linear spacetime metric. If you suppress this perpendicular direction in Minkowski TZ plane, the linearly uniformly accelerating observer looks like this kind of hyperbola, which is asymptotically reaches z equals to plus minus ct planes. So we cannot get any signals from this F region, future region. In P region, you cannot send any signal. Also from L region, you can neither send nor receive any signal. So L left and right wedges are causally disconnected. However, there can be a lot of quantum correlations between left and right wedges. Also, this right wedge is a globally hyperbolic spacetime in its own. Therefore, one observer can stick to this trajectory. One can perform quantum field theory in this right wedge itself, and one can get at the end he will get Unruh radiation at temperature proportional to acceleration of the observer. One limitation behind this setup of disjoint left and right wedges and getting this kind of global horizon for this uniformly accelerating observer is that observer has to accelerate for infinite duration. Acceleration has to be eternal. However, we know that in laboratory we can have only finite duration acceleration trajectories. Also, in astrophysical scenario, black holes have this kind of Hawking radiation, so they have finite lifetime. So a realistic observer experience horizon only for a finite time. So we will address the question that how does finite time acceleration and its subsequent return to inertial motion modifies global Fock space relations, local detector response, and information backflow and entanglement dynamics. So we consider this kind of trajectory, which is almost uniformly accelerating for a period which is determined by tau naught, and in far past and far future this trajectory is inertial. The coordinates assigned by clocks and rulers of this observer, namely eta and xi, are related to the clock's time and position assigned by inertial observer. By this transformation, observer is along xi equals to 0, and this coordinates eta and xi are also global coordinates in themselves. They cover full Minkowski spacetime, and in the limit of tau naught tends to infinity, the trajectory tends to Rindler trajectory. So if you take a tau naught tends to infinity, we will get Rindler trajectory. Since both inertial as well as accelerated observers have their own complete set of basis vectors, one can expand the real massless scalar field in terms of creation and annihilation operators of both observers, and can also write down annihilation and creation operators of accelerated observer in terms of inertial observer using Bogoliubov transformation and the Bogoliubov coefficient, which mixes positive frequency of inertial to the negative frequency of accelerated observers. After modulus sparing and integrating over all frequencies gives kind of expectation value of coefficient number, and which we can say is non-thermal. However, it is also finite for finite tau naught. If we take tau naught tends to infinity limit, which is the limit of Rindler trajectory, one gets this normalized occupation number of particles to be Planckian thermal result, which is expected. Now we know this Bogoliubov transformation calculation is global in nature, and it doesn't tell what does an observer which lives for finite duration detects using a detector which is also localized in space-time. So for this we introduce this kind of two-level system called Unruh detector system, couple them linearly to the real massless scalar field. Its dynamics can be described by this kind of master equation, where H effective is effective Hamiltonian and LO is dissipator, which depends on heating dissipation and dephasing terms, with gamma i's are respectively absorption rate, emission rate, and dephasing rates, and they are determined by correlation functions. So if you think of dynamics evolution to be described by this kind of dynamical map, then if every intermediate step of this map is completely positive, this dynamics is CP divisible. For our case of unreadable detector, if all gamma i's are, if gamma I is, any of these gamma i's are less than 0 for any moment, we say CP divisibility has been lost, and the dynamics become CP indivisible, and the phenomena of information backflow may take place, since they are determined by this response rate. So we take this interaction Hamiltonian, where phi is the field, the massless scalar field, mu is the monopole moment of the detector, chi is the switching function, and lambda is a small coupling constant. In adiabatic approximation, in the approximation where g prime by g square is less than 1, one can expand this response rate like this, where first term is thermal Planckian contribution, and on top of that we have some corrections. In the limit of high frequencies, high compared with acceleration, so omega by g tends to infinity, one can approximate response rate like this, and first term here is exponentially small in the limit of omega tends to infinity. So we see that when particle is going from acceleration phase to inertial phase, while decelerating, this g prime will be negative. As a result, response rate can become negative. In the limit omega by g tends to 0, one can approximate response rate like this, which is a quadratic function of frequency. So we see that in low frequency region also we can have a band where response rate is becoming negative. This tells us that, like, due to finite duration of acceleration, we have CP indivisibility, and that may exist this information backflow information from environment to ancilla detector system. In intermediate frequency region, one can evaluate response rate numerically. So we do here, and here dotted lines are response rate for eternal Rindler, which is acceleration for infinite duration or time. We see that this during the phase of almost uniform acceleration, the response rate is quite well matching with eternal Rindler, while in far past and far future, the response rate is 0, while in between it can become negative. And when does it become negative, and for how long, it depends on parameters, all parameters like detector energy gap, tau naught, as well as acceleration parameter. Here we fit with the analytical approximation. We see that those approximation was quite good. Also, complete positivity variation is quantified by, if any of these P1 and P0 are negative, complete positivity can also be validated. So these are physically ground state probabilities with initial condition 1 and 0 respectively, and they depend on excitation and sum of excitation and de-excitation terms integrated over from initial time to time observation. So we see that when we keep twice of frequency greater than acceleration scale, then this P0 can become negative. So at frequency scale, twice of frequency is greater than acceleration scale, we see there is a violation of complete positivity also, and hence dynamics can become completely non-Markovian. Okay, now next interesting question we take do entanglement harvesting, in which we take two Dubey detectors, place them in space like separated region, couple them to a common environment, which is real massless scalar field here, since field here and here is basically entangled. With time evolution, both detectors, even if they were initially non-entangled, can become entangled with each other. Since they do not communicate with each other, it means entanglement, whatever they get, is due to entanglement already present in the field. So we initially keep both detectors in separable state, time evolve with the same interaction Hamiltonian and trace out field degrees of freedom, and then we get this kind of reduced density matrix final state, where diagonal elements represent characterize transition probabilities, while M and M star characterize non-local correlations. They depend on pullback of White-1 function along detector's trajectory and this ion propagator. We quantify entanglement between both detectors by negativity, and apart from entanglement, there could be various other types of correlations. So we quantify total correlation by mutual information. Detectors can also get entangled just by communicating with each other, which are not intrinsic property of the field. So we quantify this signaling estimator by this commutator term integrated, and we perform entanglement harvesting in the parameter region where this signaling estimator is minimum tends to 0, so that maximum contribution comes from intrinsic property of the field. So first we take one detector along this inertial trajectory and other along this accelerated trajectory. Acceleration could either be eternal or a finite duration acceleration trajectory that I showed. If tau naught is large enough and we perform entanglement harvesting during almost uniform acceleration region, we see that like we get some negativity like eternal one, and we get in the case of this when inertial detector is in the right side, so we perform when this is far away from this crossing regions. So in this region we say there are two peaks in negativity as well as mutual information. We take Gaussian switching. Tau naught is the peak of the Gaussian switching, and if also with increase of acceleration parameter, the negativity decreases in the right side, while if we put inertial trajectory to the left side of the accelerated one, we see only one peak, and with increase of acceleration in the left side, entanglement as well as total correlation, mutual information increases with the increase of acceleration. We see the reason later. Now, if we consider inertial trajectory to be like an ensemble of inertial trajectories with Gaussian peak centered at a fixed constant proper separation from the accelerated one, we see this kind of plot. Here also we see that with increase of acceleration in the left side, this transition negativity and total correlations are basically increasing, and we also see that the entanglement measure integrativity is not depending on whether dynamics is Markovian or non-Markovian for this finite duration acceleration trajectory, because here dynamics is non-Markovian, here Markovian, we can get same kind of plots. Of course, in this region of parameter space. Now, those results might be completely dependent. Sorry, the relative dynamics between both detectors also. So we take two static detectors, static with respect to each other, so that there is no relative motion between them, and put them in front of a moving mirror. Now, if mirror is along this trajectory, we have this kind of energy density, energy flux. When energy flux is minimum, we see there is a peak in negativity. When this energy flux is maximum positive, the entanglement measure, this is negative. This is minimum. And if we consider mirror to move along this kind of trajectory, then this mimics the Unruh kind of radiation. And since detector is in the right side, we get the same kind of negativity entanglement measure like what we saw using inertial detector and one accelerator detector, and inertial one is in right side of accelerated one. And here also we get that negativity is decreasing with increase of acceleration parameter. So that result could be due to, we could conclude that increase of temperature of radiation bath in right side is basically decreasing entanglement, while in left side it is basically increasing. So this is summary conclusion. So I can stop here, and if there is any question I can take.
Thank you so much for the talk. Do we have any questions from the folks here on Zoom?
Yes, Nitesh, thank you so much for the nice talk. I really like the organization and very clear diagrams. So my question, I guess, is, the first finite time acceleration mirror, I really like this idea of using finite time acceleration because it removes the pathology of infinite acceleration in the far past and far future. And I think you can really get some nice insights. So I really like this procedure that you're using, but I'm curious whether or not you've checked if the trajectories you've chosen go to rest in the far past and the far future, or whether they go to some constant velocity relative to the lab frame. So in other words, you can have that finite time acceleration, but are you moving at a constant velocity asymptotically, or are you coming back to rest? And I think I missed that. Can you maybe help me?
Yeah, understand? It is moving at constant velocity in far past and far future, but it is inertial. So yeah.
Oh, it is moving at a constant velocity in the far past. And it's, are they the different speeds in the far past and the far future?
Yeah.
Oh, they're different.
It could be different. Yeah.
Okay. Or you just have a parameter to tune that.
Yes.
Okay. Oh, interesting. And that's where is that where you get most of the memory, or is it, if it goes back to rest, you don't get a memory effect?
More is coming because of, like, even if you do not consider this kind of trajectory, just G prime, if G prime is getting negative. So this result, what I showed, let me show once again, just 1 second. So this result is not specific to our trajectory. So for a very large class of trajectories in adiabatic approximation, and when G prime by G square is less than 1, if we can ignore higher orders, then one can approximate response rate like this. Then for any sufficiently smooth trajectories, if G prime is getting negative, if detector is going from some acceleration, so deceleration phase, then this term will become negative. And here this term is exponentially small if omega by G tends to infinity. So yeah, CPU divisibility will be lost if this trajectory is getting decelerated.
Okay, I see. So it depends upon.
Yeah, there is also few approximation, like we consider initial state to be fully separable and initially it is inertial. So with those approximations, for a large class of trajectories, if the trajectory is decelerating at some instant, then CPU divisibility will be lost. Yeah, and information back from may take place.
Okay, thank you. Helps a little
thanks.
bit. Yeah.
So I will stop sharing if there are no questions.
I actually do have a question I'd like to ask. So just to related to Mike's question, it's because so what you have is that a detector is at first moving inertially in one direction, then accelerates and changes the velocity at the end, right? So this is basically it's moving in one direction, then it's going to accelerate, and it's going to end up moving in the opposite direction, I'm assuming. I mean, it doesn't have to be that way, but I'm assuming that is the case. But I guess the
moving around only one direction.
Okay. So it starts moving in a direction that accelerates very hard, and then it keeps moving in that direction.
Yeah. This is same as like Rindler one. If you take very large tau naught, then it reduces to Rindler, eternal Rindler trajectory.
I see. Yeah, no, because
this dotted one is Rindler.
No, yeah, because I was about to ask basically the how did you choose the trajectories? I mean, it was certainly not because of how pretty the expressions on the slide look. So it's was there a specific reason for choosing these? Do these really help you with the numerics, or like what was the logic behind choosing this shape for the specific shape for the finite acceleration trajectories?
Yeah, so our motivation was that we wanted one trajectory, smooth trajectory, which And if you take tau naught tends to infinity, it should reduce to regular trajectory, and this gives us a global coordinates which covers full velocity space time, finite time horizon, no other motivation.
Okay, I mean, there are infinitely many trajectories that satisfy that, but still, it's a I do wonder how it chose the specific log of Koch, but
there are many results also valid for other trajectories also. So one we take specific for the field.
okay, but very good. Well, thank you so much.
Yeah.
All right, so I'm pretty sure that the next speaker is already here. He's just been asking questions. So Mike, you just muted yourself, huh? So I'm not sure if you intended to do that.
Here we go. Let's see if I can share.
That would be helpful.
This. All right. Is it visible?
Yes, it's now visible. Yeah, okay. So the next speaker is Michael Good, and Michael will talk about particle creation from entanglement entropy. So to compute it from bit, please, the floor is yours.
All right, thank you, Rick, for the introduction, and thank you, Arnab and Nitesh, for tuning in. So the main question I'm trying to answer is whether or not time-dependent information flow can be used to create particle count. I'm interested in information creating matter. Okay, so this is kind of a question that John Wheeler asked in 1989 when he was interested in it from bit. And a bit of a metaphysical paper, but what I think I've done here is meant to be a small step forward in this program where we understand the physical observables from an information perspective. So this is some work done with Evgeny Yevlev, who's at University of Minnesota, and Eric Linder, who's the director of the Cosmological Institute at UC Berkeley. So a little bit of an outline here is that I don't think John Wheeler is be that happy with what we've done, because what we're looking at is a continuous profile of information, S of t, and he was really into a discrete information, yes or no questions to get the observables. But we're not going to address whether the fundamental substrate of the universe is discrete or continuous. We're just going to use a continuous trajectory, and then for the output, we're going to get particle count and energy emission and particle spectra. So the first order of business is to just check some trivial cases and see if things are consistent, and make sure there's no pathologies. Then I want to look at a moving mirror example, very simple, a black hole analog. And then I'm going to look at real world accelerating electrons. In the case of small particle production, we're going to try to amplify it and get large particle production for harmonic cycles. And we're going to look at infrared and ultraviolet behavior as diagnostics. So the main point I want you to take away from this is that we're going to start with an information profile, and then we're going to end up with particle count. So that's what we're looking at. And we're doing this explicitly, okay, analytically and exact. So the it is particles, and the bit is entropy. And the entropy that we're going to use is what's often called geometric entropy or von Neumann entanglement entropy. Now, of course, there's lots of different types of entropies, and just because a quantity is called entropy doesn't mean it's the same as another quantity that's called entropy. So this is a well-known, established von Neumann entanglement entropy from 1994 from Frank Wilczek and others. Derived in conformal field theory. It's the quantum version of Shannon entropy. And in particular, for the moving mirror model, which is massless, scalar, it's in lower dimensions, and there's no curved spacetime, it turns out that the entanglement entropy is proportional to the rapidity of the mirror itself. So take a moment and think about that. What you've got on one side is information, and on the other side, you've got the kinematic equation of motion. So you got kinematics on one side and information on the other. And so rapidity is additive in relativity, right? You might remember from your special relativity that you just add rapidities to different reference frames. which is what we do intuitively for a non-relativistic regime. And of course, entropy should be additive because multiplicities are multiplicative and the log of multiplicities are additive. So it's really nice that rapidity and entropy have a nice relationship here. The 1/6 just comes from conformal field theory. It's normally a 1/3, but since we're going to have an accelerated boundary cutting space into two pieces, you get a factor of 2, so it becomes a 1/6. And this negative sign you pick up is just based on the direction in which the trajectory is going to be moving. So if it's moving to the right, we say that it's positive. If we move to the left, we say it's negative. So yeah, so this moving mirror is imposed upon the equation of motion after you've solved for the equation of motion, and then you can exactly solve for field observables. So I'm a little bit ashamed here to say that I couldn't do this relativistically. So I'm going to have to resort to non-relativistic physics. And that's a big trade-off because there's a lot of interesting physics that are associated with high speeds and relativity, especially with respect to black holes. But there is a good advantage for this is that, well, the math becomes ridiculously simple and it becomes physically intuitive in many ways. So what we're going to do is just deal with trajectories that move pretty much slower than about 10% the speed of light. And we're going to call the entanglement entropy the velocity, all right, negative velocity over 6. And you'll see that if you want the equation of motion for the particular trajectory, you just do an integral over the information profile. It's a very simple integral. So the procedure here is that we're going to start with some information profile. We're going to go to Fourier space, Fourier transform, and go to frequency space. And then from that, we're going to go to the particle spectrum and the particle count. So this is always going to be in the non-relativistic regime. That's our regime of applicability. And so this is a low entropy or low information regime, everyday life type of information. So they're interchangeable input data, if you will. So if you turn the crank with this acknowledgement and just start looking at the moving mirror model in terms of information rather than kinematics, then this is some of the answers. These are some of the results. And you can see that the beta Bogoliubov coefficients, which is what you need for particle production that we saw from Nitesh, is pretty much just the entanglement entropy. All right, so there's some factors of frequency, P and Q, out in front, but it's effectively just the entanglement entropy squared. When you integrate over the correct out frequency, then you get the particles as a function of P, the P frequency. So the transformation here is between the in and the out vacuum, and those are defined by the field modes, which are plane waves in the far past and the far future. And so in order to get the total particle count and the total energy emission, then you just do an integral over the information as a function of omega, with a single omega out in front for the particle count, and omega squared for the energy. So what is omega here? Well, it's the conjugate to laboratory time, but it's actually just P plus Q in the moving mirror model. So it's really just a variable that we've transformed to do the integration simply, but it does have a physical meaning in the sense that it's the Fourier frequency conjugate variable to laboratory time. So you can see it's just a simple integral. If you got an information profile that you can square and that you've gotten from a Fourier transform, and you can integrate it over the frequency, then you've got the particle count and you've got the energy emission. So these are the integrals that we want to do, and we're going to actually do it with a few profiles just to see if we know what we're doing and to test consistency and look for some physical insight. The stress energy can also be done in the time domain, which gives you an independent check to make sure everything is correct. So this is the derivative of S with respect to T, and you square it and you integrate over all time. And this energy better be the energy above it for the particle energy. So stress energy better equal the particle energy if we want Parseval's theorem to work out and the model to be consistent. So these are the answers. So this is what we're gonna use, and we're gonna test this with a couple of particular information profiles. So in order to get these integrals to be finite, we got to make sure that they're convergent in the infrared and the ultraviolet. Now, the ultraviolet regime is easy. This just diagnoses smoothness. If the mirror jumps around, appears at one place, and then instantly appears in another place, then you've got a discontinuity and you're going to have an ultraviolet divergence. So I've never studied discontinuous moving mirrors or jumping moving mirrors. It sounds like an interesting direction to look into, but I want these integrals to be finite for this particular exploration, and so we're gonna make sure that the mirrors are always smooth. Okay, for infrared convergence, we need to make sure that there's no overall change in information. All right, so that gives us asymptotic rest. So the mirror comes back to rest in the far past and the far future. So this is a nice finite particle emission. So this gives us a nice convergence. Now you can still get compute situations where, say, the change of information is a constant, and then you'll get a divergence in infrared, and you'll have soft particle emission. But if your change of information is infinite, then you'll also have soft particle production. So the IR is at the minimum a diagnostic of purity, and you can see that kinematically we need the mirror to come to rest, and informationally we need there to be a delta S be 0, right? No change in information. So it's got to be a nice page curve that goes back to 0. So this is the diagnostics in the infrared and ultraviolet. And so now we're ready to try a few trivial profiles, right? A static mirror gives off no radiation. So there's no particle count, there's no energy. It's pretty easy. A constant velocity mirror has energy is 0 as well. And, you could just boost to a reference frame where a constant velocity mirror is static. So you better hope that there's no particle emission either. But there is a soft particle divergence. So you can see that some soft particle emission, this infrared divergence, is just a result of your reference frame. So there's a support at omega is 0. But this is an expected pathology that we would hope to see if we have a constant velocity mirror. So now in eternal acceleration, which uniform acceleration here, that's going to go real fast. It's going to have not one but 2 horizons. So this is outside the regime of our non-relativistic regime. But nevertheless, we could just set the entropy profile to a linear dependence on time, and with a regulator and results that are independent of the regulator, we find that the particle emission goes to 0 when we remove the regulator. So the energy is always identically 0. So anyways, these are the kind of behaviors we expect, and we have demonstrated consistency with our non-relativistic results here. And so now we're ready to move on to something non-trivial. So the first profile I'd like to share with you, I'm really excited to share with you, is a nice small smooth information pulse, a Lorentzian profile. All right, this is a common profile in Fourier analysis because the Fourier integral can be done very easily. It's this t squared plus 1 all squared on the denominator. And we're going to have the maximum entropy that the mirror achieves at some point in its trajectory to be much less than 1/6, which corresponds to low entropy. This corresponds to a mirror that has a velocity that's much less than the speed of light. So it's a slow mirror, right? This is a very slow mirror. And the energy is finite. It depends upon the parameter of the system. There's only one parameter, dimensionful parameter of the system, that's kappa. Kappa has dimensions of acceleration, if you will. And the particle count has the same prefactor, except it's dimensionless, which makes sense. Particles are just ticks of your particle detector. They have no units. And what we get is a nice new formula that says that the more information that you have, this maximum information that you've obtained along your world line, the more particles you have. So more information, more particles. Increase the maximum by 2, you increase your particle count by 4. So this is relatively intuitive. Maybe it takes more information to get more particles. But nevertheless, this is a completely finite example, analytic and exact, and gives us a nice place to start. So again, this starts and ends at 0 entropy. So overall, there's no change in information here. Okay, so let's move on to the second example, which is a black hole analog. We can look at a low entropy profile, which we approximate to be small entropy, that has been studied before for a black hole analog. And we were going to replace kappa with mass, where kappa is the surface gravity for the black hole. So 1/4m is kappa. And this is the time profile you can see here as an incomplete gamma function. Well, if you didn't know, you can take a Fourier transform of an incomplete gamma function exactly. You get a function called the Dawson function. And it's very simple, and we've got it in terms of omega here, S of omega. F is this Dawson function. And you can integrate this in our previous integrals and solve for the energy, the particle energy, like all the energy of emitted by each of the particles added up. And we get the energy is the mass. So this makes sense because we would assume that if we have a completely evaporating black hole, that the total energy of emission would be the mass of the black hole itself. It's even easier to confirm this in the time domain because you don't have to do a Fourier transform or any of that. You just integrate this incomplete gamma function and you get the same thing, energy equals mass. So since we're doing this consistently, we have confidence that we can compute the total particle count, which depends upon mass to the 4th and can be done exactly. It's proportional to the Catlin's constant, which I'd never heard of before. I'd done this problem. And so we see that bigger mass black holes give off bigger amounts of particles. However, keep in mind that there's a trade-off for this complete evaporation example, and that is it only works for small masses because we're in the non-relativistic regime or the low entropy regime. And so the mass has to be much smaller than the Planck mass, which means that this is not going to apply to astrophysical black holes, which contain a lot of information. And thus, this is only for black holes, with mass less than that of a mosquito. But nevertheless, it is an interesting analytic example that demonstrates complete evaporation and finite particle count. So if you're worried about it being small, this whole machinery can still be used to amplify particle production by just going over many cycles. So for instance, if you use a sine wave for your information profile, you can then do many different cycles and say even at 10 cycles, we get something that's very close to, visually close at least to infinite cycles, where the spectrum can be solved for exactly. And the answer is extensive in the number of cycles. So it's just 12 times the number of cycles times s squared, where s is the maximum speed of the trajectory. Or if you convert to information, it'd be like the maximum information of the trajectory. So this is a finite amount of particles that can be large, a large amount of particles. The energy is always 6n times s squared times the dimensionful parameter of the system. So we can get a large amount of particle production. You even get the same answer if you dampen the sine wave. So it's actually pretty neat that you actually get the same particle spectrum and particle production. So now I want to mention very briefly that you can see that this is going to be more general than just a moving mirror, right? So if you think in terms of information, you could imagine instead of a perfectly reflecting mirror, you could modulate the index of refraction of the mirror, right? So it's like semi-transparent, and you could simulate kinematics, right? So information perspective is different than the kinematic perspective because maybe you have a situation where you're not actually moving and there's nothing physical moving, but you do have a change of information. So as long as you have an expression for the entanglement entropy, then you could still compute observables. So to that end, I'd like to look at the accelerated electron case, where now I'm going to I want to say that in the early 80s, Wald and Unruh and Ford and Vilenkin, they found some hints that the accelerated electron was very similar to a moving mirror. In fact, there is an exact map between the two. It's a duality, exact one-to-one correspondence between the two models. So this is a 1+1 dimensional model where you have production of massless scalars in the moving mirror. It's a quantum model. And then you have a classical model in 3+1 dimensions of photons, spin 1, and there is a one-to-one map. So if you know the trajectory of the mirror, you know the same trajectory of the electron, and you can compute all the observables. So it's in flat space for both of them. So it's not a gravitational duality or anything like this, but it is, two dimensions up. And we suspect that since there's this perfect map between the two, that there is some sort of information profile for the electron, which we could call, proportional to the rapidity, and which we call this electron entropy, and it has a time profile that's dependent on this product log. And so we're going to choose this particular trajectory, this particular information profile, because it gives the same energy as beta decay. So we know the energy of radiated beta decay when an electron goes accelerating off from its parent neutron and produces photons. We know the energy of those photons. It's been calculated in QED as well as classical electrodynamics. And we found the profile that gives this energy. Well, when we end up doing a Fourier transform of it and then compute the photon spectrum, we get a Planck distribution. Now we weren't looking for Planck distribution. We weren't looking for thermality. This just kind of popped out. We didn't order this. And it seems a little bit strange and certainly interesting. So it's a 1D Planck spectrum. And keep in mind that radiated beta decay is not in equilibrium. There's no Boltzmann equilibrium. There's no maximum entropy. It's not statistical mechanics at all. This is out of equilibrium. Nevertheless, we get this Planck distribution. Okay. Well, it turns out that this can be done relativistically. So we can actually find that trajectory gives if you plug it into relativistic classical electrodynamics, you can integrate the power, you could integrate the photon spectrum, and you get the same result as inner Bremsstrahlung from beta decay. And all we have to do is identify the scale of the problem, the dimensionful scale, with the kinematic scale of beta decay. That is kappa is 12 over pi E max, where E max is the amount of energy available to the electron. It's just the mass of the neutron minus the mass of the proton minus the mass of the electron. So it's 782 keV. So we get a nice temperature of the photons from the Planck distribution. We're defining it through the Planck distribution. So the mass of the neutron, this difference in mass is equal to pi squared over 6 times the temperature of the photons. The temperature here is fixed. It's eternal. It's always the temperature since the photons are always in a 1D Planck distribution. It's 10 gigakelvin, which is about the temperature of the big 1 second after the Big Bang. So it's not cosmologically hot. A lot of processes have happened in 1 second, but it's definitely room temperature hot. So the kinematics fixes the scale, and we have looked at the data from RDK2 experiment at NIST. They were so kind to give us the data, and we're very proud of the fact that we just simply plotted our 1D Planck spectrum with the fixed kinematic scale, which is no room for fitting, and it goes right over the data for radiated beta decay. So we have found that beta decay is a one-dimensional Planck spectrum. This is a classical acceleration thermality, or an information thermality, if you will, since we could start from the entanglement profile, or a kinematic thermality if you start from the classical equation of motion for this particular electron. So this is one experiment. It's not a high energy precision physics experiment. It's only about 3 sigma. And but nevertheless, it is a confirmation that beta decay has a one-dimensional Planck spectrum for its photons. So, well, my colleague thought that this was neat, that was interesting, but it's really just, he just thinks it's a coincidence, right? I mean, it's just a Planck spectrum, it's 1D, but, you know, there's nothing much deeper because it's not in equilibrium. So I was looking for a reason why this would be, you know, where the kinematics are that's interesting, that that signifies this. And it turns out, I can tell you that there is something a little bit satisfying, is that it turns out that this information profile is left invariant if you add an imaginary time period to it. And the inverse of that time period is the temperature of the photons. So this is imaginary time periodicity in the source, not in the field. It's not KMS periodicity. This is in the equation of motion or the information profile. So in that sense, a little bit of a better explanation. So to sum it up, I just want to tell you that you can think of matter creation as coming from information. This is it from bit. And we can get a large amount of particle production from amplification. We've looked at a mirror, we've looked at a black hole, we've looked at accelerated electrons. And when we looked at beta decay, we found a one-dimensional Planck distribution. And this is some work that was done with Morgan Lynch, that he's given a talk in a couple of hours. So I'd really like to thank him for a lot of his work, especially some of this experimental analysis. And he's the guy who got the data from NIST. So I need to appreciate that. So thank you for your time.
Second, there you go. So thank you so much, Mike. And this is actually amazing. It's I'm very, very happy with the how far you managed to connect things using this idea of the matter creation from information using the entropy. So I have a couple of questions. So it's just I mean, sure that the entropy is a great quantifier for information, like in the sense of the information loss and all this, but or just uncertainty. But do you think it's really like something special about the entropy, or do you think that you could also find some other quantifiers that are somewhat related to information, but that, I mean, it's like of course if you change something, you change the information flow, you change the matter content, you change things, right? And these things are correlated, right? So it's are there some other let's say quantities that you think that could also be used to draw an analogy or to infer the particle number, or is really information, the entropy, special in this sense, would you say?
Yeah, no, I don't think it's special. I mean, not uniquely special perspective, because we can do it kinematically. We did it kinematically first. So if you just take the equation of motion of the electron, you assume it's like a little baseball. That kinematics has an imaginary time periodicity. And so that was pretty weird. And there's lots of trajectories that can have imaginary time periodicity, but this is the one that has a linear piece that makes the Fourier integral convergent. Mm-hmm. And it's the one that gives one-dimensional Planck distribution that's exact and analytic and relativistic. But when you put it in terms of information, you see that the information is invariant. So I would say that maybe the perspective that the information is left invariant, that could be unique. But this is a really nice question. But thankfully, we can look at it from both a motion, a kinematic point of view, and an information point of view. And I'm hoping that this. I'm hoping. See, it's also a bit speculative that the electron has an information profile, because that came from conformal field theory and the moving mirror. And so I'm really just kind of following the same analog from the mapping duality. And I'm not sure if it has any kind of utility outside of this particular model, or even outside the moving mirror. So that's a little bit speculative, just the fact that the electron itself would have an entanglement entropy that's the same form as that of conformal field theory. Because electrodynamics is not conformal field theory, right? So, but yeah, it's a wonderful question. That's going to make me think about how unique that is. Yeah.
I mean, just to ask you something else, it's I mean, when you started talking about this, the first thing that came to mind was, well, you should try to use this to handle black holes and all this, which you did, right, up to some extent. Of course, there's the limit of the mass. So I guess that my question is, like, what would it take to be able to apply this formalism to push the regime, say, in the black hole case, or to push to higher masses, and to really say, hey, you really can entirely think of the matter creation from black holes as the entropy all possible scenarios, and maybe even apply this to more fundamental theories and all this. So the question is basically, how hard is it to push the regime of the in the black hole case?
I think it's possible. I don't know why I'm optimistic about it, but I mean, I can find higher order corrections, right, perturbatively, relativistically. Okay, it's not really that interesting, but I bet that there must be a clever way to do this, because some of the mathematics is so simple that I bet you there's an ultra-relativistic way to do it. I mean, that would be the first start. You don't have to do it relativistically for all speed, but ultra-relativistically, maybe there's a way to do it. Me and a couple of colleagues, we looked at it for a little bit, but I don't think we put in more than 10 to 20 hours. And I would imagine that it probably, I'm optimistic that it could be done, because I would really love it. But I did, every time I did it, I was like, man, there's no way, I don't know how to move forward with this integral. There's an integral that you have to look at, and it's like, what do you do with this? I can't solve this integral. But maybe for okay, look, in principle, that electron, it's relativistic, right? So there are certain profiles that can be done, right? So that certain, if you're okay, maybe not in generality, but if you're okay with picking a very specific trajectory, or very specific profile, and then doing it then yeah, those can be done.
Maybe you can start from there and then try to generalize or perturb or something. That'll be nice to see too. Okay, good. So, and just last question, it's not really a question, but next week you will be at the Thermality and Quantum Field Theory Conference in Brazil, right? Okay, great. So we're going to see each other there, so hopefully we'll be able to chat a little bit more. Yeah, for sure.
Oh, wonderful. Well, I'm going to give pretty much the same talk, so I'll try to change it up for you a little bit.
Well, then by then I'll have other questions, I'm sure. All right. Okay. Well, Mike, thank you so much. All right, so let's thank Mike again. And now we go for our lunch break, and we'll be back at 2 p.m. European time. Convert that, or 12 GMT. Convert that to your time zone if you're watching online. And feel free to join the speakers. If you want to join back the link and ask questions and all that, feel free to do so. All right.
See you, Rick.
Okay, great. Welcome back to the second session of the RQI Circuit Online. So here is the first speaker. We have Morgan Lynch, and he'll talk about hyperbolic recoil and the Unruh effect at CERN. So this is a very interesting research line in which experimental data from these big labs is used to connected with fundamental physics. So please, Morgan, the floor is yours.
Thank you, Rick, for the invitation, and it's a pleasure to speak with you guys again. As you said, this is the work I was looking at with hyperbolic recoil and the Unruh effect at CERN. This was carried out when I was at the Max Planck Institute in Germany. I'm back in the US now, and I would like to explain to you a little bit about the work I did when I was out there. And so kind of to begin, just a little bit of an overview. So we'll be looking at some channeling radiation experiments from CERN. This is the NA63 experiment, where we were able to find some signatures of the Unruh effect there. And so we did various analyses of this experiment so far, right? We first off looked at an Unruh DeWitt detector analysis way back in 2021 during my postdoc when I was at the Technion in Israel. And then following up on that initial analysis, we started looking at the Unruh effect in various ways. And another one that we did, which I presented in Lisbon a couple years back, was assuming that the particles which comprise the Rindler bath are little microscopic black holes. And so we were able to do kind of a dual Hawking analysis of these data sets. Likewise, whenever you have the Unruh effect present in a system, there should always be an associated Rindler horizon. And as you know, like if a Rindler horizon or a generic black hole event horizon, if I throw particles into it, the area of the horizon will change according to the change in mass or change in energy. And so you can do this dual Rindler horizon analysis from the particles that are being emitted in this Unruh setting. And so this one was published just last year as well, where we did our dual Rindler horizon analysis. And then while I was at Max Planck, what I did was, so I had been looking at these experiments from the point of view of like the Unruh effect community, using Unruh DeWitt detectors and black holes and Rindler horizons and things like this. But these experiments were originally proposed and designed to explore radiation reaction. And so when I was at Max Planck, I was working closely with Karen Hatzagortsian to learn all the techniques and tricks from the radiation reaction side. And so what I did is I learned those tricks and found where the Unruh effect can take place in the radiation reaction theory. And that is the subject of this talk right now. This has just been published in PRD. It's a free paper online. Max Planck pays for their papers, and so you can there's no paywall for this one. And so just in general, we're looking at particle physics experiments. So I like to say QED in curved spacetime, but basically what we're using is the high accelerations from these radiation reaction experiments to explore quantum field theory in curved spacetime. So just to begin, let's go a little bit of the background of these channeling radiation experiments. Their first experiment that they looked at was this 178.2 GeV positron experiment, which were fired into samples of single and amorphous crystal silicon. This was a very big Nature communication paper that came out. And just to give you a little bit of idea how these experiments work is you basically have a positron beam from CERN. It penetrates through a couple scintillators and magnets to give you particle identification and beam energy and things like this. And then it enters their crystal. So this is a single crystal of silicon. So you have the regular atomic array. These particles will penetrate the crystal and oscillate transversely as they scatter off the atomic sites, emitting photons. The initial positron beam is bent out of the way with a magnet, and then you have a converter foil, which this thing, what it does is it converts that initial photon that's emitted and converts it back into an electron-positron pair, and so you can do the particle identification. But this converter foil also filters out 2 photon or 3 photon or higher order events, and so this what it does is it ensures that you get a single photon spectrum. And to give you an example of this power spectrum, these black data points are the measured power spectrum of these photons that are emitted, and the colored curves here are the kind of standard catalog of radiation reaction models that you see here. So this is the kind of spectrums that we'll be looking at. To give you a little bit more details about these experiments, okay, one of these key features that you see is the field strength that you get here. So if you consider the critical strength or the Schwinger field limit, you have this electric field 1.3 times 10 to the 18 volts per meter. Okay, now if you want to think about the experiment in terms of these crystal structure, right? If you think about the Coulomb field that is near the atom, right? So you have some 1 over r squared electric field that you have associated with these atoms. And so for a silicon atom, you have an atomic number of 14. And then if you look at just the lattice site, the lattice constant for silicon, you have something about a half a nanometer, right? And the electric field strength, or the critical field strength, is given by this parameter chi, where you have a Lorentz factor of gamma. Again, this is for a transverse electric field. So you have these atomic sites. It's the transverse electric field, which the electron or the positron feels as it scatters. And it scales as gamma. And for ultra-relativistic scenarios, this gamma is what brings you into the critical field strength here, right? And so if you consider gamma from these experiments around 3.5 times 10 to the 5, an effective distance from the Coulomb site, you know, about one lattice constant, to say 1 over 10 of a lattice constant, this field strength goes from 0.02 to about 1.8, just to give you an idea of the numbers that we're dealing with here, right? And it's the fact that you get over 1 here, over unity. So this is when you expect things like the Schwinger limit, or Schwinger effect, excuse me. And this is kind of associated with Hawking and Unruh effect, but it's this parameter and the fact that this is of order 1 or above 1 that gives us access to things like Hawking or Unruh radiation or Schwinger type of effects in these systems. And this is why we start to look at radiation reaction from these. And so just to look at, going back now to high energy synchrotron emission, all right, which is how we would look at in radiation reaction. When you look at these experiments, you have a transverse positron, or a positron oscillating transversely, right? So it's a harmonic oscillator in a transverse position. You can consider this as just being a generic cyclotron motion, okay? And when you look at, or when you think of radiation reaction in these sense, you can have a cyclotron circular oscillation with the emission of a photon, which leads to an in-spiral to a smaller radii. And what we want to look at here then is instead, we want to look at the emission of these positrons where the recoil from this photon emission, then we incorporate this hyperbolic recoil trajectory. So the Unruh effect comes from the acceleration, which comes from this recoil, okay? Now, the quasi-classical recoil that we'll be considering is associated with this in-spiral here, right? And the way this is incorporated is actually really cool. I never knew about this, right? So if you consider, say, a generic photon field, which goes like some plane wave, e to the ikx, likewise with the positron or electron fields, right? So generic plane waves with some spinners. If you look at the interaction, so you have the photon field, which is wedged in between the two operators of the electron, right? And the trick then is to commute the photon field, to use it as an operator, which you move all the way to the left, and by commuting that, using the commutation relations, you transform these p's, you use it essentially as a momentum translation, right? And so p minus k, so these things already starts looking like recoil, and it's a quantum mechanical recoil, which comes specifically from just commutation. And so this is this quasi-classical technique, okay? That people had been using to incorporate recoil traditionally. So whenever you hear about synchrotron radiation reaction or all these other radiation reaction techniques, it's this cool way of this commutation trick. And then what I did was I just looked at a generic cyclotron motion and then just included a hyperbolic recoil just by relativistic velocity addition into that trajectory, okay? And in both cases, what we want to do is just look at a standard photon emission. With the one quasi-classical technique, we incorporate recoil by commutation. And then with the hyperbolic recoil, we incorporate recoil by including the hyperbolic trajectory just into the trajectory proper. And so looking at the radiation in that sense, one of the first things that we need to do in terms of looking at Unruh effect is how much time we have that to accelerate so we have time to thermalize, okay? Now, this has been traditionally a very difficult thing to find for the Unruh effect is the thermalization time, right? So if you have some excitation rates, you need to reach detailed balance for excitation to de-excitation, and the thermalization time is just 1 over the excitation rate. And this has been traditionally difficult. But what we can do is we can compare processes. So we're going to look at an asymptotic analysis of the radiation, comparing synchrotron to this Unruh hyperbolic recoil. And so when you look at a generic radiation interaction, right, your photon matrix element just basically gives you some plane wave. Our charge current has your velocity into it, characterizing the velocity. And so with your amplitude, as we just move through, ignoring all the factors out front, you just have the v dot a, or the velocity dotted with the plane wave of the photon. And what we want to use is the method of steepest descent to look at the asymptotic spectrum of this thing. So what we want to do is just take the derivative of this phi, set it equal to 0. This gives us this condition of 1 minus beta squared equals 0, which normally you wouldn't have this because you can never go faster than the speed of light, but it gives you imaginary solutions. And it's these imaginary solutions of time which we're going to be considering here. And so what we have then is the coherence time, which is defined by this factor 1 over omega with this 1 minus beta squared here, evaluated at T1. T1 is the real component of this solution. And then the imaginary component is what's known as the formation time. And the high frequency, or the asymptotic limit of this amplitude is basically an exponential decay of e to the minus the formation time over the coherence time. And just to give you a little bit of an idea, the formation time, as you can imagine, as this particle is accelerating, the photon will build up around it. That's the formation time of it. And then you could have multiple photons that all get emitted coherently, like in phase, and that's the total coherence time of these things. So formation for one photon, coherence of multiple photons emitting coherently. And then the asymptotic spectrum is just the square of that amplitude. And so you could look at basically any radiative process by just looking at the by computing that solution, that imaginary solution, and you can get the asymptotic spectrum for these radiation emissions. So what we're going to do is apply that to both our synchrotron and our hyperbolic recoil scenario. Okay. Just with this relativistic velocity addition, it factors into the solution for both the z component as well as the hyperbolic recoil component. Okay, we get our imaginary and real components, the formation time and the coherence time for both scenarios here. And then what we want to do is we want to compare, okay, where the acceleration time, so the Unruh one, has a higher power than the synchrotron emission. So that means that you have two competing processes, but this gives us a threshold on the acceleration wherever the Unruh effect one starts to dominate. And you get this really clean critical frequency at the beam energy divided by 7. Below, photons below this energy, it's just pure synchrotron radiation, or the power spectrum is dominated by synchrotron. And above it, it's dominated by the recoil acceleration. So it's dominated by the Unruh effect. And here for these acceleration, we use a generic omega squared over m recoil acceleration, okay, to compute these numbers here. But at the end of the day, what we get is this threshold is e over 7. So now we want to also look at this thing from the point of view of conservation of momentum, okay, just to give you an idea of where we can pull out more accelerations here. So considering our velocity addition, we see that just at the low time scale limit, this just reduces into a generic velocity addition formula, okay? And what I want to do is I want to multiply this formula by the initial energy or the final energy of this photon to solve for basically P final equals P initial minus omega. So this factor here in red is the photon frequency. And we can do it by characterizing the initial or the final momenta. And this enables us to solve for the initial and final rapidity, okay? And then by summing over these rapidities, we get this final state rapidity here. And this gives us a generic final state rapidity as a function of momentum and energy. So we can encode a conservation of energy and momentum into these. And there's a reason why I'm showing you this. And so looking at solving for the acceleration, okay, we'll have our formation times that we can look at. So what is the acceleration that we get without conservation of energy? What is the acceleration we get with conservation of energy? Okay, so without conservation of energy, we have the initial and final energy being the same. We have our formation time here, and we reproduce the acceleration, the omega squared over m that we got in our asymptotic analysis without conservation of energy though, okay? But when we include conservation of energy, we get a different acceleration, which just scales as omega over gamma, and this is the one that we want to use to incorporate the recoil acceleration with conservation of energy in our hyperbolic recoil, okay? And which is interesting is because I've been using this omega squared over m, which is without the conservation of energy in my previous analyses. Now we have the explicit conservation of energy in our lab frame computation here. Okay, so now let's develop the power spectrum. We look at our QED interaction. And basically all we're doing is from the standpoint of computing the power spectrum, we have our V.A interaction. And what we want to do is we want to incorporate that recoil via that commutation that we did with that quasi-classical solution. And this is just a kind of standard result where we just plug in our velocities. We have a little bit of the, every time you see an E final, that's E final equals E initial minus omega, where you have that recoil correction in there. And we just plug in our various velocities and delta x's, which characterize our trajectory. Notice this isn't written in terms of the lab frame difference and final times. Okay, normally this is when you do Unruh effect, you're looking at proper times. This is a pure lab frame calculation. And so let's look at our trajectories, which are characterized by a hyperbolic recoil. Okay. And so what we have now at the end of the day is, let me see. So we need to develop our what is it? Taylor expansions of our velocities. Okay, so the v squared term that we have here expanded out to 1 over gamma in our velocity using that relativistic velocity addition of the synchrotron formula with the hyperbolic recoil. Okay, so these two formula for both the velocity as well as for the position, we just simply plug into our radiation spectrum. And it's written in terms of these standard Airy functions. So this is normally what you see in terms of radiation reaction. And what you have here is when you look at the the actual spectrum here. You have this parameter A naught, which characterizes our channeling oscillation frequency, as well as our acceleration. So if you want to look at pure channeling oscillation, set the acceleration to 0, or if you want to look at pure Unruh, you can set the omega equal to 0, or you can have a dual scenario where you can see both, but it's characterized by this A naught parameter here. So you can shut one off or the other. You could also include the quasi-classical recoil by setting, or this E final is equal to that E initial minus omega, or you could set E final equal to E initial to get rid of that as well. So this encodes the quasi-classical approximation, regular standard classical synchrotron radiation, as well as the hyperbolic recoil, all in this theory by setting each of your parameters equal to 0 or however you want, okay? And so this is what I was describing here, okay? So we have that critical frequency at omega over 7. This is where we expect that Unruh scenario to take hold. And all of the parameters and all this theory is now completely fixed by this beam energy, okay? We have our channeling oscillation frequency, which is also set by the beam energy. We have our critical frequency set where the Unruh effect dominates. And so with all of these parameters fixed, you can compare how these all look to each other. So red is the one with the Unruh effect here. Okay, what we see is an enhancement above the synchrotron, which is the blue here, and the quasi-classical recoil actually is smaller. So typically when you have a recoil correction, you get a high frequency cutoff. And what we have is a high frequency enhancement due to this Unruh effect now. And so what we want to do that was compare this to all of our data sets, okay? We have, I believe this is going to be 5, 6, 7 data sets, okay? So initially we looked at 178 GeV beam, the initial data sets. There's a 3.8 and there's a 10 millimeter crystal. So if you look at both of these, what you see is above that frequency cutoff, you have that saturation of that Unruh effect in the high frequency tail, okay? The low energy spectrum is just going to be some synchrotron emission, which our theory does not describe, okay? But you can see how the high frequency spectrum is kind of locked in. There's no free parameters in this theory, by the way, okay? And so this is what it looks like for the 178 GeV beam. Now for a 50 GeV beam, and we have our chi-squareds as well, okay, at the bottom. So for the Unruh effect, we have 1.38 and 2.1 for these crystals. And now for the 50 GeV beam, we have a 1, a 2, a 4.2, and we have 2 6 millimeter crystals. And I'm just going to cycle through these so you guys can see. Again, the low frequency spectrum is different, but that's where our theory doesn't apply. But in the high frequency tail, we see that it saturates all these data sets, okay? And that's with that hyperbolic recoil. And so it's that enhancement and the high frequency tail that we associate with this Unruh effect or with this this hyperbolic recoil, okay? And so just looking at all of them combined, you can see that with that spectrum fix, it's just basically the shape of these things where you expect the Unruh effect to dominate. Below, our theory doesn't describe it, okay? But above it, that's where that Unruh effect dominates. And in general, just by averaging over all of the chi-squareds, 0 fit parameters, everything is entirely fixed by that beam energy. We have a chi-squared per degree of freedom of about 2.12. Okay, and then so now, where does this all fit into? Okay, so that's not a problem. Yeah, no, so the 50s are all extra slides. I only have a couple more slides to go. So we're good to go. So now to look at our brief history of radiation reaction and the Unruh effect, how do these fit into each other? Okay. When you look at the Unruh, radiation reaction, there was 2 types of recoil that people have been looking at. So there's in spiral that we typically see with like binary black holes or any sort of radiation emission where you expect the particle to fall into the center. And there's also undulation. So as a particle emits, there's this 1 over gamma cone that'll emit, and so it'll undulate as it moves around its trajectory. And then it could also in spiral. But this led to a violation of conservation of energy and momentum in synchrotron emission, which was found by Richard Liu. And to fix this, what they had found was that the resolution was to incorporate a new type of radiation reaction, which is known as guiding center recoil. So in addition to the in spiral and in addition to the undulation, what you have is the entire cyclotron motion shifting as the particles get emitted. And this is what's known as the guiding center recoil. And basically what I did is I assume that there's going to be this hyperbolic, recoil that's associated with it, and you get these recoil currents from that center, and that's associated with a new essential source of current, a new source of photon emission, okay? And then to give a little bit of how this looks, Richard Liu incorporated that into the Landau-Lifshitz radiation reaction, okay? Computed, say, for a typical cyclotron, synchrotron magnetic field to give you your rotation. You have this cyclotron frequency as well as an acceleration parameter which characterizes this motion. And this gives you these equations of motion, okay? First of all, you see just the standard sine cosines, as well as these exponential decay. So you have exponentials in these from the recoil, right? Which is what you would expect for something hyperbolic. And here you could see the guiding center recoil live in effect is normally what you'd have is this guiding center recoil, the center of oscillation at 0 and 3.5. So 0 and 3.5, which is kind of way up here somewhere. And as the photon's emitted, it kicks the entire center of this rotation down to a different location, and that's that guiding center recoil that we see. And then whenever you look at the spectrum from that, okay, well, first things what we can do is we can look at the low time limit and see that there's a similar velocity profile, and from that we can match that with our recoil acceleration. And by matching these standard QED parameters, specifically the strong field QED parameter, we can get that recoil acceleration written in terms of fine structure constant and then the strong field QED parameter. Now, we overestimate this a little bit. We get about 337 compared to what we would expect from the experiment of about 1.4. But this might be due to things like the asymptotic analysis that we were doing. But what you see from that generic radiation theory is an enhancement compared to the dotted line here in the high energy spectrum, and then the low energy spectrum also a depletion, okay? And this compares to the data that we have, and this red line here is this Unruh theory, so we see that enhancement as well as the depletion, but our theory doesn't describe that in that lower energy portion. So you see the salient features of this Landau-Lifshitz theory compared to what we did with this hyperbolic recoil. And so in general, what we're finding is that the acceleration that's produced by this hyperbolic recoil, this guiding center recoil, in the low energy, or excuse me, in the high energy portion of the Landau-Lifshitz radiation theory, is it where we get this Unruh effect or this hyperbolic recoil above that critical frequency. And people had seen that you can get, this is the CERN guys analyzing their data sets where they were to verify the Landau-Lifshitz equation. We were able to connect the Landau-Lifshitz equation to that guiding center or hyperbolic recoil, and as well as analyze it that way from the point of view of the Unruh effect. And so then now, just to kind of close things off, we found this Unruh effect with this recoil acceleration, these high energy channeling radiation experiments. Using this asymptotic analysis, we were able to look at these new timescales, which is actually a new and interesting way to look at where the Unruh effect takes hold rather than thermalization time. So the asymptotic radiation analysis was something that was new to me learning this, which ended up being pretty simple and pretty robust, getting these this low frequency or this high frequency cutoff, okay, where the Unruh effect will dominate. And so this is one thing that was really interesting that we were able to find. And we found that in the Landau-Lifshitz radiation reaction theory, the Unruh effect is present in the high frequency tail. So that's the connection between radiation reaction and the Unruh effect. The first order correction of radiation reaction is Landau-Lifshitz, and the high frequency tail from guiding center recoil, that's where the Unruh effect lives. And just a little bit of prospectus about particle physics and the Unruh effect. We've seen the Unruh effect at the radiation reaction experiments at Na63. We've also seen Fooling-Davies Unruh effect, moving mirror effects in these radiative beta decay experiments from NIST. And just to show that Unruh effect is present in particle physics. And that's kind of the end of the message. And we've been able to find it in radiation reaction experiments. And that's it. That's what I got. Thanks for listening.
Thank you so much, Morgan. This is a very, very nice talk. I'm assuming that we have a question from Mike.
Thank you, Morgan. Great to have your talk. It's a really nice and exciting to see all the data. I was wondering if you might tell me maybe a few more words upon this imaginary time periodicity and the thermalization time. Maybe does the period form, or in exactly how is that imaginary time periodicity related to, say, the temperature of the Unruh effect in this context?
So that's a good question, actually. I never thought about the imaginary time formulation as it relates to the temperature. That is a very, very cool point. One thing that I can say about these timescales is, like, as an example, when you look at the solution, right? You have the real component. Basically, the idea about it is, so if I'm doing a radiative experiment, right? T1 is the time. So I start my acceleration. T1 is the time that the radiation starts being emitted. So it's basically how long it takes for the radiation to be emitted, and the formation time is how long it takes for that process to occur. Okay, now the fact that it is imaginary is exactly what you should see to define your temperature. And the interesting part is it does end up in it's up in the exponent. So I don't know how that would actually relate to the temperature, because in principle, that imaginary time should give you that periodicity, which relates directly to the temperature. That's something that I could look into, but that's a really, really good point because it should be directly related to the temperature based off that periodicity. I haven't thought of that actually.
I mean, it looks like this time period is associated with maybe the source or the trajectory of the electron, right? I'm reminded of the KMS periodicity, which is usually the field. So I'm wondering, there might be some relationship.
Is the imaginary time, is it beta or is it 1 over beta? Is it proportional to the temperature or 1 over?
I think it's the inverse period is the temperature. Yeah.
Okay, so then I guess I mean, it might flip it to the downstairs. So it might actually put itself in the correct location in the exponent. My one concern was looking at it is because it's upstairs, and so normally the temperature is downstairs. So like I might look more into that. That's a really good point though. That if there was a connection between that and the temperature, because that KMS condition with the imaginary time is something I didn't think about whenever I was looking at these things. But the fact that it's the inverse might put it in the correct place in that exponent there. So that could be something really interesting to look at. And it's really simple formulas too for analyzing these things. It's just the stationary phase approximation. So this might be a really cool project to look into, to be honest.
Okay, thanks.
Yeah.
That's amazing. Okay. Well, Morgan, thank you so much. I would ask you a question, but we're already over time a little bit. So maybe we can leave it for the next time that we can interact. And thank you so much for the very nice talk. I think this whole research line is amazing. The idea of relating fundamental physics
the kind
with
words,
this
and I appreciate being able to share the research with you guys. So yeah, thank you very much.
No worries. Okay, thank you. So now I guess that you can stop screen sharing, and I think that the next speaker is already here. Karol, you can start screen sharing and turn on your video. That's perfect. Okay. Maybe you can unmute yourself just so that we can test the audio.
Hi.
That
So
is
I hope now
perfect.
you see the screen perfectly.
Yeah.
The presentation.
Okay. Yeah, so everything is good. So just introduce you.
Great.
And okay, good. So how should I pronounce your last name?
Karol Sajnok.
Sajnok. Okay, muy bien. Very good. Okay, and so now we have Karol Sajnok as the second speaker of the session, and he'll talk about the relativistic reason for quantum probability amplitude. So please, Karol, the floor is yours.
Thank you, Rick. I'm glad to share some results from the work that I did with Andrzej Dragan and Kacper Dębski from the Institute of Theoretical Physics of University of Warsaw. And this talk is basically about the paper that we published in this year, in which we claim that the Feynman rule that you sum complex amplitudes and then take the squared modulus follows from free natural assumptions on relativistically invariant probability functions. And the outline was going to be as follows. I will first show you just the claims, then we'll go quickly through the proof because proof is quite simple, amazingly, and then we'll jump to some open questions and discussion about what is problematic still with all of this framework. Motivation basically is that in the quantum mechanics, the probabilities are not obtained by adding probabilities, but you have to add amplitudes and then you take the modulus squared of the sum, and this is the probability. And in the Feynman path integral prescription, the amplitudes are exponentials of the action along paths. However, why exactly this kind of form of that you have to take an exponential of some quantity with imaginary number reconstructs the quantum mechanics is still a problematic thing, and it's not quite understandable why. And before I jump to the three claims for probabilistic theory, I will just quickly go through an introductory work. So this was an original paper from Arthur Eckert and Andrzej Dragan from 6 years ago, in which they claimed that you can reconstruct quantum mechanics from relativistic theory by introducing superluminal observers. There are a few thought experiments in this paper, which I will not go through all of them. Here you can see the reference if you'd like to check it, but the simplest one is that when you take a look at the picture A, so when you look at a particle, at a source which emits a particle, then this particle is reflected from the mirror and is detected at some point D. Then when you look at the same space-time scenario from a superluminal point of view, then basically the x-axis becomes vertical, the CT axis becomes horizontal, and this like mirrors the image along the x equal to y axis. And then when you look at this scenario, it looks like from the mirror, the particle follows two paths simultaneously to both source and to the detector. And this argument claims to show that just from introducing the superluminal observers and claiming that the theory has to be relativistically invariant, then you can reconstruct this weird behavior that we know from quantum mechanics. What we are going to do now is that sorry that it jumps so much, that we take n alternative spacetime paths, we calculate then some invariant, relativistically invariant quantity along this path. The simplest one would be proper time along chosen path. And then we create a function with n arguments of those proper times along n paths. And we want this function, we want to force some conditions on this function in order for it to, first of all, those conditions have to arrive from probabilistic theory, and second of all, at the end, we would like this function to give exactly the same result as the Feynman sum rule. And it turns out that you only need three assumptions. Those three assumptions are pairwise Kolmogorov additivity, time symmetry, and bias rule. And let's start from the assumption number one. Basically, when you take the standard Venn diagrams, so like this school play that you draw those circles and areas where they intersect, and you use the inclusion-exclusion principle, the classical Kolmogorov probability rule looks like this: that the probability of sum of two events is equal to probability of this first event, probability of the second, minus probability that both of them happened. And in standard classical theory, this term that both happen at the same time does not appear, in the sense that when you have a particle which propagates on a path, it cannot, in classical theory, propagate on two paths simultaneously. And however, when you go to the quantum mechanics, this can change, and this second order interference term is present. However, it turns out that in quantum mechanics, and this was basically the result of the work of Sorkin, you cannot have interference of more than two alternatives simultaneously. And in the language of those, basically, when you take this first equation over here and you assume that all the higher order interference terms vanish, then you can rewrite this using the Venn diagrams or some algebra in this kind of condition, which is given by the equation number 5, which tells you that the function of n proper times has to be equal to the sum of all of the two paths contribution minus some contribution from the single path terms. physically, it arises from the fact from the 2 and 3 slit experiment interference experiments. Basically, when you look at the picture C and picture A and picture C corresponds to the same situation. The probability or the shape, the interference pattern when 2 slits are open is not equal to the summing of the patterns from having 1 slit open or the second slit open, basically because of the fact that this 2 slit interference term is non-zero. However, when you look at the interference pattern with 3 slits open, then this is exactly equal to summing all of the 2 slits open contributions and subtracting the 1 slit open contributions. And all of the higher order interference terms also are reducible to the 2 paths or 2 slits interference patterns and 1 slit interference patterns. This was proven experimentally up to very, very high precision, and in the current understanding of quantum physics, there is no higher than second order contribution interference. However, of course, you can consider some higher order theories, but it's not the point of this work right now. This was a new assumption. The next 2 assumptions are taken from the work of Andrzej Dragan and Artur Eckert. And those 2 assumptions, first of all, is the Bayesian composition. So when you have a particle that travels via some point P, then the probability has to be equal to multiplications of the contributions from those 2 regions. And this time symmetry tells you that when you change the time order, the direction of time, the probability has to be exactly the same. And you can see all of those conditions on the schematic. The first one is the pairwise-Kolmogorov additivity for the 3 paths. The second is the time symmetry. The third is the Bayesian composition rule. And the theorem of the paper is that when you take those 3 conditions for any function of n arguments, then you reconstruct exactly the Feynman sum rule. The proof is very simple, actually, quite simple. And we'll go through it because I think it's quite nice. So the step 1 is that we take a 1 path sector. So we take the bias rule, this one, question number 7, or the plot with 3 stars for n and m equal to 1. This is the Cauchy multiplicative functional equation. It has an only single solution, which is an exponential. However, when you force the time symmetry condition, so not only the condition number 3, but also condition number 2, then the only solution which satisfies both of them is a trivial solution in which P1 is equal to 1 always. So this is a start. And this tells you that the derivative of Py in 0 is 0. Then we can use the fact that the derivative of P1 and 0 is 0 to use the standard definition of derivative, and then look at the case in which we add a constant shift to all of the arguments of the function simultaneously. So this is the bias rule of m equal to 1, but n arbitrary. And this tells you that it's invariant under shifting all of the arguments simultaneously, because P1 is always equal to 1. And when this is just a statement. You can rewrite this analytically, but that's not the point right now. It's in the appendix if someone wants to. However, what we will take from this is that when you take only 2 arguments, then both of them, it turns out that, and you apply the time symmetry, you can rewrite the function of two arguments just in terms of the function of a difference of them. And this function has to be time symmetric, so it has to be an even function. This is just a simplification of notation. However, now the whole problem, at least at the level of 2-point functions, is translated in a single function instead of having two argumental functions. And this is precisely the fact that now we can take the step 1, we can take step 2, and we can use the pairwise additivity rule and simplify it in this form of equation 18. So it turns out that not only the two-argument function, but the n-argument function can be explained in the terms of a function of the difference minus some constant. And now, when you look at the equation 18, and when you take the bias rule for any two components, you can write a functional equation. And in the simplest case, we just take both n and m equal to 2. The P4 function of all of the sums is explained as the multiplication of two P2 functions. And when you rewrite this using this equation number 18, you arrive with a functional equation for the function d, which can be solved. And it turns out that this functional equation is the D'Alembert equation, which has only three solutions. The trivial solution with equal to 0, cosine or hyperbolic cosine. This finally gives us a solution for the function d, so the two-argument function. It turns out that it's equal to 2 plus 2 cosines of some constant kappa, which multiplies x, and x was the difference of two proper times on two paths. And this is basically the end, because now we can plug this back to the pairwise Kolmogorov rule, and after some algebra, it turns out that you arrive exactly at this Feynman sum rule. Of course, in the meantime, you would have to do an assumption that you want your solution to be bounded, to discard this hyperbolic cosine branch. And this is what we do, because we want the probabilistic function to be a bounded function, normalizable. And because of this, you have an imaginary factor in the exponential. So this is basically the claim. When you take the proper time equal to action, which is exactly the fact that relativistic action is equal to proper times mc squared with a minus, and you set this kappa function, arbitrary function, kappa constant, sorry, to 1 over h bar, you arrive exactly at the Feynman sum rule. However, the problem is that this whole so let's just okay. Sorry, I forgot about this part. Just about the role of all of the three assumptions. The bias rule helps us to understand what does it mean to create a composition when the particle, for example, we know that the particle travels through some small region in space, and we can tell that the probability of traveling between this point is equal to multiplication on two paths. The time symmetry is useful because it creates from the beginning the exponential behavior, and sorry, the bias rule forces the exponential behavior, and the time symmetry forces the evenness of both the two path function or single path function, and in the end the n path function. And the new condition, so the new result from the work of 6 years ago of Dragan and Eckert, is introducing this pairwise additivity Kolmogorov rule, because without it, then the family of all solutions is very vast, and it does not reconstruct exactly the Feynman sum rule. And when you take this condition additionally, turns out that we exactly get only those solutions. So with those three conditions, there is no other solution for the function that describes propagation over n paths, apart from, of course, this hyperbolic Cohen branch, which is unbounded, so it's not very useful to describe probability. The new thing because basically it may be just another reconstruction. So one nice thing about this reconstruction is that instead of all of the others that I'm familiar with, you do not assume anything about the Hilbert space. You do not assume the complex vectors. It just magically appeared from the conditions which can be easily understood in the language of relativistic or probabilistic description. The interesting thing and unanswered yet is why the reality actually ends at the second order interference. So why we do not observe the higher order interferences, and this is not I do not have an answer for this. It's an interesting problem. Why? Maybe there is some deeper reason. And two maybe different issues are the fact that this reconstruct all of the quantum mechanics. It reconstructs the massive Klein-Gordon equation. However, in that form, as it was written in the paper, it does not reconstruct the gauge freedom and the Maxwell equations, so you do not get the underlying spin of the photon, and basically the Maxwell equations. It can be this prescribed in this sense that instead of taking the path history, you take the field histories, and then you just use the action for the Maxwell equations, the classical Maxwell equations, and you get exactly the same. So this is quite, let's say, easy generalization. However, harder generalization is the Dirac equation. And of course, this is just basically the problem of the Feynman reconstruction of the Dirac equation, that of course you can get the Dirac equation using, for example, Grassmann variables. However, this is, in my opinion, it's not an elegant reconstruction, because the Grassmann algebra is like an ad hoc choice of non-commuting structure to get the Dirac equation. However, the deeper issue is how to do this with a purely classical theory, and this is like another of the open questions, and hold the derivation. And this is basically all. Thank you.
Very good. Thank you so much, Karol. Do we have any questions from the Zoom audience? Because if not, I do have a question. It's more of a comment, I guess, but maybe you can also help address it. So it's very nice how you can recover interference from simpler assumptions and all that. I really like the way that you presented it and how few assumptions are necessary to recover these things, right? The behavior of particles, let's say, in quantum mechanics. But when you consider quantum mechanics, like, sure, the big novelty is that you can consider superpositions that involve these complex phases and all this and all that. But I do think that, for instance, when you start considering quantum field theory, the big novelty starts arising when there are no particles at all. When you're in the vacuum, when there's no particle for you to try to path integrate over paths of particles that are going from one place to the other, and things like this. And of course, it's possible to recast like vacuum correlation functions in terms of paths of particles and all that. But I was just wondering whether, how to connect these formulas that you presented with, say, vacuum correlations or something more quantum field theory. Like, can you apply this when you have no particles? I guess that would be my question. When you only have a vacuum or some sort of like global state that is entangled between regions and all that.
This prescription is basically just a mathematical rule that when you take a function of n arguments, those can be any n arguments, and you force those three conditions, then you reconstruct something that looks like equation number 34. So when you take a field theory, a classical field theory, and you use some invariant quantity for the field for the classical field theory configuration in the some phase space or some configuration space for the field, then you can reconstruct just using some mathematical condition. However, you lose, of course, this understanding of the path integration over paths. These are no longer paths in space-time. These are some paths in the field configuration space. There is a hole for sure for describing the quantum field theory in this description. However, this is like the same hole that we have in the Feynman sum rule prescription for the quantum field theory, I believe.
No, yeah, okay,
but
fair.
Yeah, this is an interesting thing.
I mean, let us know if you ever figure out how to implement quantum field theory and really recover all of relativistic quantum mechanics, let's put it this way, with this formulas. But it looks very interesting to be able to start from very simple assumptions about how correlations and probabilities behave and reach results that in principle rely on more than that, but now we get more and more to see that they don't. So that's very nice, very nice. Very nice talk, Karol. Thank you so much. So let's thank you again.
Thank you.
And I guess that now we can move on to the next speaker. The next speaker is Samuel. I'll like.
Yes, can you hear me?
We can hear you, yeah, 100%. But maybe we should start screen sharing just to make sure that everything is working.
Yep. Does that work?
It's loading, which means that probably it's going to work within a couple seconds, and we're going to be happy. So just give it a second, because sometimes Zoom takes a while to really connect and then share the screen. There we go. Now we have it. Okay, good. So our next speaker is Samuel Fedida. Samuel Fedida. And he'll talk to us a little bit about foundations of relational quantum field theory, scalars. So please, Samuel, the floor is yours.
Great. Thank you very much for the invitation first. And it's a great pleasure to present some of the work that I've been doing with Jan Blavatsky, who's now in ISRQI Vienna. It's based on the preprints, where we look at, we revisit the foundations of quantum field theory, trying to incorporate some aspects of relationality and operationality and use some of the new tools coming from quantum reference frames to understand where quantum fields emerge from a more axiomatic point of view, and sort of revisit the foundations of this theory. So let me go do a brief introduction, motivation of quantum reference frames here. I'm going to talk about one type of quantum reference frames. There are many in the literature. I'm going to talk about operational quantum reference frames. So say you want to describe a physical quantum system based on the system Hilbert space HS. Now, we assume that you're already an agent. You're already in the description. Okay, this is an operational approach. It's not trying to describe what agents are. Agents are, and you describe what they have access to. And so, in particular, imagine that you want to describe a system, but you have access to clocks and rulers, okay? And in particular, you might want to think about this in some sort of philosophy of measurements, where any measurements can fundamentally be boiled down to position and time measurements, okay? So this is a very fundamental idea, but okay, let's work with clocks and rulers. These in classical physics, or even in standard quantum theory, are representatives of idealized reference frames, tetrads, really. And you use them to understand the properties of the system, like position, time durations, velocities, and so on. Now, in the lab, clocks and rulers are physical systems themselves. If I want to use a clock and a ruler to describe another system, I need to put them on the table. I need to manipulate them. These are quantum systems. And as quantum systems, they have some degree of quantumness. Maybe this quantumness is completely negligible, but maybe it's not. So this is the idea behind quantum reference frames. Now, for the purposes of this talk, I will consider a quantum reference frame to be a specific type of quantum system, one that can assign probabilities in a way consistent with a given symmetry structure. What I mean formally is that it's a triple where you have a reference Hilbert space. So remember, we had a system Hilbert space, and now we have a reference Hilbert space as well. You have a group, a locally compact group G, which has which acts unitarily on the reference Hilbert space through a weak star continuous projective unitary representation. And you have a normalized covariance P of M. Now, this P of M takes as inputs Borel subsets or measurable subsets of some space sigma, and sigma is a value space, okay? But we take sigma here to be a torsor for G, okay? So it's a bit like G, okay? It's G and a point. You can really think about it as if it was G, okay? The nuances are irrelevant for here. So how do you understand this ER? Well, this ER really generates these probabilities, these quantum probabilities consistently with a symmetry structure. This is where the covariance comes from. You can understand these ERs as generating Born property measures. Okay, so if you prepare your quantum state in a certain state, your quantum reference frame in a certain state omega, this generates a Born property measure. Okay, this is canonical. All right, so let's have a look at the specific type of quantum reference frames we're going to be interested in. This is what we call a relativistic quantum reference frame, where the group is the proper orthogonous Poincare group, and sigma, so value space, is the orthogonous orthonormal frame bundle over Minkowski. Okay, here we work on flat spacetime for now. The curved spacetime generalization is incoming. But so what this space is, what this value space is the space of tetrads. Okay, it's the space of really reference frames, inertial reference frames. So this is a principal bundle with Minkowski as base space and Lorentz as fibers. A point in this space is just a choice of clocks and rulers localized somewhere at a point in space-time with a given orientation, Lorentz orientation, so orientation and also rapidity. Okay, now for a quantum reference frame, okay, what you have now is that when the quantum reference frame is prepared in a state omega, this gives rise to Born property measures of clocks and rulers of reference frames. And so now you have a property distribution, a Born property distribution over this space. Okay. Now this property distribution projects down to Minkowski spacetime, to the base space, and just like how in the classical case, the localization, so the projection is the localization of the tetrad, we can now say that the localization of the quantum reference frame when prepared in the state omega is just the projection of this property measure. Okay. Now, once we have quantum reference frames, you might want to describe the system HS, okay, relative to this quantum reference frame. And this is the subject of relativization maps. So suppose you want to understand what joint observables of the system and of the frame look like. Okay, and this is given by the following map. Okay, it's the Yen map. And you can understand this as a G12, okay? But it's a G12 that is well-defined for locally compact groups. And the right-hand side is here Poincare invariant, okay? This is just highlighting the fact that relevant or physically meaningful observables are fundamentally invariant under the symmetry structure. This is you can understand this as saying, the absolute position, for example, of a particle is not meaningful, is only the relative distance that is meaningful between two particles, and the relative distance is translation invariant. Okay, so this is in this sense that it's meaningful observable to look like. Okay, now if you condition this observable on the state of the frame, what you get now is this restricted relativization map, which is now an operator in the system Hilbert space. So it's a bit like saying, if I have access to, or if I prepare my clock and rulers in a certain state, okay, what does the observable that I'm interested in of the system look like relative to this preparation, okay? And this is the right-hand side. Again, it's like a G12, but now weighted by a Born property measure given by the frame. Okay. Now, we can ask a very similar, but very slightly different question. If you fix now the observable, or the operator that you're interested in, the system operator, and you know the properties of your quantum reference frame, you can say, well, what happens to this observable when I prepare my quantum reference frame in a given state? Okay. So for example, I can say, well, maybe if I prepare it here on Earth, it's going to look like a certain thing. But maybe if I prepare the quantum reference frame on the Andromeda galaxy with a certain rapidity and so on, the observables are going to look very different. Okay, and how different it is given by this map, the relational that we call the relational scalar quantum field. Okay. So the right-hand side is just the relativization map applied on phi, but now it has a different domain. The domain is you choose the state of the frame, okay, and it outputs a system operator. Okay. So now the question, of course, is how does that relate to the usual notion of quantum fields? Well, we can use some mathematical tricks. Okay, it turns out it's always possible to decompose this Born property measure. More generally, you have what's called Markov cardinals, but here, let's not worry about this. Here, you can decompose your property measure into a conditional measure and a marginal measure. So the conditional measure is a measure on the Lorentz fibers at every point x of the base space, and the marginal measure, mu fr omega, is a marginal measure on the base space, on the Minkowski spacetime. Okay, and you can show that this itself is a Born property measure. Now, this decomposition allows us to define a new quantity. Okay, a new map. We call this a relational local quantum field, and this now takes points in spacetime. Okay, and in particular in the support of this marginal measure, and outputs an operator. And it turns out that this field at every point x I'll put the averaging at the point X over the fibers. So if given by the frame. Okay, so if we go back to the picture here, what you do is that you translate your operator phi at the point X, and then you average over the fibers. Okay, and this is the quantum field at X that you would want to associate. Now, when you do this, and it turns out after that, what you can do is also write this marginal measure as a function times the Lebesgue measure. This is, again, always possible. You can show that, and it's very, very easy to show, that your relational quantum fields are given as smearings of these pointwise quantum fields, smeared by the marginal measure, the function that, that you get as a marginal measure. Okay, so now this looks a lot more like the usual notion of quantum fields that we're used to. This is literally the same definition as we had before, but we can show that we reduce to this. Okay, and again, we can talk about the localization of the quantum reference frame in a state omega as the support of this function. Now we're making a lot of progress in trying to understand how this notion of quantum fields associates to other notions of quantum fields, like in Whiteman QFT. Okay. First, let's look at some properties of these fields. As I said, we don't have an invariant notion of observables anymore because you've conditioned on the state of the quantum reference frame. From invariance, we get covariance. Okay, once you fix the omega. Okay, so we get the right sort of notion both algebraically and analytically for both the kernel, so the pointwise fields, and for the Smeal field. Okay, so this is all good. And one thing, so this is covariance. I should say, this means that if you act with an active transformation, a Poincare transformation on the system, it acts also, you can see it as an action on the frame. Okay. In standard practice, traditionally we say, well, this says that there's a duality between active and passive transformations, but now really even the passive transformation is itself an active transformation in some sense because the frame itself is a physical system. Okay, this is just words though, so just take it as the maths tell you in some sense. Okay, so from covariance we can go to causality as well. And let me briefly mention some ideas there. We have relational notions of causality, but first I want to highlight that for me, causality is something that is deeply epistemic rather than ontic. Okay, it's about what you can see rather than what is underlying your observations. And I would argue that one could and maybe should limit the notions of causality you work with to something like operationally meaningful preparations of the frame and operationally meaningful notions of space-like separations. Okay, so for the first one, for example, you can be interested in frame preparations such that, for example, the supports that you get are compact. Okay, so maybe this is compact in the frame bundle, but you can also look at different definitions where it's compact in space-time, for example. So if you do an experiment at finite times in the finite region, okay, this is something that can be interesting. Another idea for point 2 is that maybe you are not interested in really understanding causality to the finest precision possible mathematically, because maybe fundamentally you can't access things like space-like separations that are less than a Planck length, for example. Okay, maybe you are fundamentally, in terms of your resources, you are fundamentally limited to what's to a minimal space-like separation, and so this is not a new idea. Okay, there's this notion of smeared light curves that you can introduce. Okay, so something is sigma space-like separated if it's space-like separated plus a little sigma. Okay, for example, a Planck length. Okay. Good. Now, from there, we can define certain notions of causality for your quantum fields, for your relational quantum fields. So if you have, for example, 2 quantum reference frames, R1 and R2, okay, so imagine I'm here and I have a colleague on the Andromeda galaxy at space-like separations. I have a clock and rulers. They have a different clock and rulers. I prepare it in a certain state. They prepare it in a certain state. Let's look at this the space-time marginals, if the space-time marginals are space-time separated, then maybe I would expect a non-disturbance condition. Okay, and this can be implemented, for example, in this Einstein causality condition. So now you see that causality is relational. Okay, it depends on the properties of your quantum reference frames. This is a property. This is not something we assume, we axiomatize. Okay, maybe some relational quantum fields that will be interesting in the future don't have this property. Who knows? Okay. However, this is typically sufficient to prevent simplicities. Okay. Now there's other notions of causality that you might be interested in. I'll briefly gloss over them, but you might be interested in things that physicists are used to, like microcausality pointwise. Okay. So if you want the pointwise quantum fields to themselves be causal in this sense, there's a strong notion of microcausality, and I'm not going to enter into too many details about how this differs to what I'll call a weak microcausality. Arguably, this weak microcausality condition is much more robust and better, in my opinion, than the strong notion of microcausality, which is what physicists are used to. But indeed, what we show is that this strong notion of microcausality that I glossed over implies the weak notion of microcausality, which itself implies the smeared notion of causality. And for many purposes, the strong notion of microcausality is too strong. Okay, so I would argue that weak relational microcausality is the right notion of pointwise microcausality. Now we have an example, for example, of weak relational microcausality inverse of Einstein relational causality. Basically, you take a free Klein-Gordon field, and you take the while operator for some function f, and you relationalize that, and that gives you a relational quantum field, which is weakly relationally microcausal. Okay. Now, I think an interesting open question is whether quantum reference frame transformations always preserve causality conditions. Indeed, because we have quantum reference frames, it might be interesting to look at QRF transformations. And in particular, if not all QRF transformations preserve causality conditions, is there a subclass that is interesting of QRF transformations that do? Okay, this is an interesting open question. Now, you might be worrying that I'm talking about pointwise quantum fields. You might say, well, what about UV divergences and so on? The whole point in Whiteman QFT of not talking about regular distributions, so distributions with a pointwise kernel, is that you have UV divergences. Okay, so is there something wrong in this? And the answer is no. Okay, surprisingly, but I guess this is reassuring. And let me talk to you about pointwise quantum fields in Whiteman QFT. Okay, and we'll make the link very strongly there. Okay, so Whiteman quantum field is now an operator value distribution. Okay, and what you can do now is define almost by hand what is a pointwise Whiteman quantum field. Okay, a pointwise kernel, and you can do this always. Okay, this is almost tautological, that you can introduce these kernels. But now these kernels are function dependent. Okay, these are function dependent kernels, and this means that you can always write your Whiteman quantum fields as a smearing of a function dependent kernel over spacetime. Okay, this is almost tautological, but it's important. Now you notice that this is dependent on the function, and indeed what we have is also dependent on the smearing function. Okay, in some interesting sense, and it actually in the same sense as Whiteman QFT. So really, this is okay. Now I defined a kernel explicitly in terms of phi of f here. You don't need to do that. Okay, there are more general kernels, and indeed, in particular for us, pointwise relational quantum fields will not be explicitly written given the smeared relational quantum fields. Okay. So we can start to compare between relational quantum field theory and Whiteman quantum field theory. One point of comparison is the smearing functions. For us, they're L1 functions. For Whiteman quantum field theory, they're Schwartz functions. So you can think of what happens as a Whitemanian limit, if you want, where the QRF maybe is very nicely behaved or maybe the state that you use is nicely behaved, then you expect something like Whiteman curve T. But in general, we extend it. Okay. You have all sorts of analogies. Covariance is analytically and algebraically the same. You can talk about irreducibility as well, things like that. Vacuum cyclicity and all these theorems also hold. One thing that's interesting to me is that causality is a bit different. So in Whiteman curve T, it turns out that because of the very rigid analyticity properties of Schwartz functions and thus of the vacuum expectation values, there's this notion of the local, of the global notion of local commutativity, which says that if you have sigma causality, then you have exact causality. And this is not necessarily true for us. Okay, so we have more leeway to find interesting examples. Again, vacuum expectation values share some interesting properties, but there's some small deviations that I won't cover here. Before I finish, let me just also make a link with algebraic curve T. We can define algebras of relational local observables and relational quantum fields. And we've shown that these satisfy the axioms of algebraic curve T. So this is another way to understand relational curve T. You can use algebraic methods for it. Okay. Good. So to conclude, I think we have shown that we can provide operational and relational notions to Whiteman axioms. For example, where do these smearing functions come from? There is now a precise sense in which you can say this is where it comes from. It comes from the space-time marginals of the QRF. Likewise, you can understand algebraic curve T in a different sense. And some interesting open questions include how to extend this to unbounded operators. For now, we have bounded operators. This is a purely technical question. It's underway. Something else, extension to curved spacetimes and gauge theories. This is a work that should be out in maybe 2 or 3 weeks in collaboration with Alberto Ibert and Arnab Mukherjee. Extensions to spinors as well is interesting. Understanding relational quantum field dynamics, relational Lagrangians and actions is something we've talked about a little bit in the paper. Understanding relational scattering theory would be super interesting, and relational renormalization as well, we've discussed in the paper. So on that note, if you have any questions, let me know. Thank you.
Thank you so much, Simon. Okay, this is very nice. I mean, I think it's a very important research program so that we can, understand what we mean when we're talking about smeared observables and algebraic quantum field theory and all this. And honestly, it's nice to have an operational way to look at these. And I'm really looking forward to more connections between the two, more explicit connections, or what is probably more interesting is more explicit discrepancies between the two, right? So you mentioned that L1 and the Schwartz differences. This would be nice to really understand where the differences, what would be the differences, and hey, who knows? Maybe we can perform an experiment and actually couple to a field in an L1 region that is not Schwartz or whatever, and then actually play with these things. That would be super nice. So on that note, do we have any questions from the Zoom audience? Because if we don't, I do have my own questions, so I'll abuse my chair rights, I guess. Okay, so there's one thing that I think that the whole quantum reference frame thing relies on, apparently, which is symmetries, right? And symmetries are very useful. They're very essential for many things, but there are some symmetries that are only they only exist locally or something like this. So for instance, everything you presented here was about Minkowski spacetime, and you were assuming time translation symmetry. You were assuming translation symmetries overall and all of the symmetries on Minkowski spacetime to build everything, right? You're assuming Poincare symmetry. So I mean, of course, if I have one field and this field interacts with another field that is in a state that is not translation variant, so say I have a box where I put my field, and this box is made out of states of other fields, right? It's very useful to be able to describe my field still without having to refer to the box or still pretending that it's symmetric, right? So in these cases, do you think that it would be possible to extend this whole formula that you have to the cases where you don't have too many symmetries? And you do have the curved spacetime thing here, which I was really intrigued by. But then let me ask a very specific question: is this extension to curved spacetimes only for curved spacetimes that have some sort of symmetry, or is this for general globally hyperbolic spacetimes? Like, what's the idea here? And how do you
It's even beyond globally hyperbolic spacetime. So thank you for the question. I mean, so this was my motivation for this new project that should be out in probably 2 weeks, I think, where we extend the notion of quantum reference frames for more general symmetries. Indeed, group symmetries are one type of symmetries, but they're global symmetries. And even gauge symmetries are a specific type of local symmetries, but they're not all the local symmetries. The real notion of invertible symmetries is captured by this thing called groupoids, okay? And groupoids are more general to capture symmetries. And in particular, you have spacetimes. Actually, generic spacetimes have a trivial isometry group, as you mentioned, whether it's globally hyperbolic or not, okay? However, there's something called the Poincare groupoid of a spacetime, okay? Arbitrary spacetime, Lorentz spacetime. And the Poincare groupoid captures the local Poincare symmetries, okay? So in the local charts, you can think of as local Poincare symmetries. And this always exists. This is always non-trivial. This is always nice. So the local notion of Poincare symmetry is captured by groupoids, okay? Poincare groupoids. And you can do the same thing for gauge groupoids, for example, where if you have topologically non-trivial spacetimes and you want to understand gauge symmetries, you can't use the usual notion of like C infinity of mg, for example. This requires a global trivialization, which is non-existent in general. But the groupoids picture always works. So arguably, you know, the right way to think about things operationally when you think of symmetries is to always think about things locally, right? We've never, strictly speaking, tested Poincare symmetry or isometry symmetry, because when you test isometry groups symmetries, you always have to restrict to a certain region of spacetime, right? A lab or something. And
all experiments are local.
To a region of spacetime.
Every single experiment is always local.
Yeah. So every restriction to a local thing breaks the group structure, but it preserves the groupoid structure. So this is the real symmetry structure that you should be interested in. So this is out in 2 weeks.
I'm really looking forward to it. Well, thank you so much. So let's thank Samuel again. This is great.
Stop sharing.
Very, very good work. Thank you so much for presenting this.
Thanks.
So I guess that now we should move to the next speaker. The next speaker is already here. It's João Caribé. So if you want to screen share so that we make sure that everything is working.
Oh, of course. Well, I'll share my whole screen because I can't find the PowerPoint screen here. Let me open it again.
You might be able to just share the whole screen and that should be enough. Typically on Zoom, that's the best way of going forward because, yeah.
Okay, let's do it. Whenever you can see my screen, let me know.
We can see it all, yes. We can see exactly what you can see. So right now we have the slides and everything. Okay, perfect.
Oh, nice.
So let me introduce you. So the next speaker is João Caribé, and he'll talk to us about mass dependence of the Araki-Ullmann relative entropy across dimensions. So please, João, the floor is yours.
Okay, so thank you for the introduction. To begin, I would like to thank the organization of the event for organizing this worldwide event. I can only imagine how hard it is to organize an event of this scale. And I would also like to thank for the opportunity to talk about my work in this very large event. So that being said, my name is João, as Rick introduced it. I'm currently a postdoc at Rio de Janeiro State University, and I work in the group of Professor Silvio Sorella, who is also from the Rio de Janeiro State University. And today I'm talking about one of our works where we studied the mass dependence of the Araki relative entropy across different space-time dimensions. So the question we wanted to answer was, maybe space-time dimensionality can shape somehow the relative entropy between two quantum states. So if it does, how does it shape and how does it look? So this is what we want to study in this work. The structure of this talk is the almost canonical structure, so I'll begin by briefly reviewing the relative entropy concept in quantum mechanics and quantum field theory, because it might not be familiar to everyone. Then I will present my setup. So I introduce the scalar field I'm using, the relative entropy between the vacuum state and the coherent state, which is the setting we used in this work. I will briefly talk about the Pauli Jordan distribution, and finally, I will present the numerical procedure that we had to use in order to compute all the integrals that appeared in this work. And then I finally present the mass dependence, and close with a couple of final remarks. That being said, let me begin. So say that we have a quantum mechanical system, and we prepare maybe this system in two different quantum states. So it is prepared in the state psi and in the state omega. In this notation, you should understand psi and omega as density operators. And the question is, I want to know how well or how easily I can distinguish these two quantum states. And one of the ways you can go about it is to compute the relative entropy between these two states. The relative entropy was originally introduced by Umegaki in the 60s, and it has this expression which might be familiar for anyone who worked briefly with quantum information. So it relies on the trace and, of course, on the density operators for the two quantum states. Now, it has two nice properties. The first one is that it is non-negative, and the second one is that it is zero if and only if the two quantum states are equal. So it is zero if the two quantum states are perfectly undistinguishable. And whenever it's positive, it means that you can distinguish the two quantum states. The larger the relative entropy, the easier it becomes to distinguish the two quantum states. And when I say distinguishing the two quantum states, I mean in the sense that was nicely captured in this quasi-quote from the work by Frobe and Sangaletti. So say that you prepare your quantum system in a state psi, and you want to make an educated guess about what is the state of that quantum system. For that end, you make several measurements. You make n measurements on your system. Then the probability of wrongly guessing that the system is in the state omega instead of the state psi decays exponentially with the relative entropy. So it is in this sense that I say that the relative entropy quantifies somehow the distinguishability between two quantum states. But all that I'm saying here is valid for quantum mechanics, because quantum field theory is slightly more complicated, because density operators and traces are not always well defined in quantum field theoretical settings. So the natural question that arises is, can we generalize the relative entropy to this case? So how can we study distinguishability between two quantum states using quantum field theory or in a setup with quantum field theory? Can we do that? Can we generalize it? And the answer is yes, we can generalize the quantum relative entropy to quantum field theory. The history is as follows. So in quantum field theory, say that we have our field prepared in two different quantum states, psi and omega. Here, the psi and omega refer to vectors on a Hilbert space and not to density operators anymore. Now, the relative entropy in this situation is given by the expression presented by Araki. So this is also called the Araki or the Araki-Ullmann relative entropy. And as you can see, the expression is remarkably different from the previous one, because here we have no traces and we have no density operators. So it is more well suited to the quantum field theoretical setup. And it also has the advantage or the benefit, to say something, that if you consider a quantum mechanical system and use this definition of relative entropy, you recover the definition I had presented in the previous slide. So this is a generalization of that notion of relative entropy. And as a generalization, it also shares the same two nice properties that I talked before. It is non-negative, and it is zero if and only if the two quantum states are the same. So one thing that appears here, which might not be familiar to everyone, is that delta psi omega. So this object is what we call the relative modular operator. And it arises in the context of Tomita and Takesaki modular theory. We can say the following. So to briefly present it, because it's not a very simple topic to deal with, there is the modular theory by Tomita and Takesaki. And the modular theory allows us to define an object, which I'm also calling as psi and omega, which is known as the Tomita relative operator. And this is the relative operator because, as you can see, the action of the relative operator somehow relates the two quantum states, psi and omega, while also taking the adjoint of the operator it acts on. Now, to actually see where the relative modular operator comes from, we have to apply the polar decomposition to the relative Tomita operator, and from the polar decomposition, we obtain an expression and the definition of the relative modular operator. But this definition isn't very simple to work with for practical, concrete computations like the one we want to perform. We want to get a number out of the expression for the relative entropy. For that end, it is simpler to use the expression derived by Longo, which is equivalent to the expression by Araki. However, it is easier to deal with this version of the relative entropy than with the original incarnation of the relative entropy. So this is what we are going to use in this work. So this was the relative entropy. So now, how we set up the state and the field and everything in order to compute it. So we consider a massive scalar field as usual. This is a simple massive scalar field. So I expand it in superposition of the creation and annihilation operators. Just a remark, we are working with a massive scalar field, so the dispersion relation is slightly, well, less trivial. So we have the m² term. And then you impose the canonical commutation relations, and very briefly, that's it. We have now our quantum scalar field to work with. The issue here is that the field operator, or what is written in the first line of this slide, isn't actually an operator, but rather an operator-valued distribution. In order to obtain an operator out of it, we have to smear it against a test function. So the actual field operator is the smeared field operator, which is defined like that. So it is the operator-valued distribution is mirrored against the test function, which I'm calling f. And for the purpose of this work, we consider f to be compactly supported and smooth. So this is the setup of the quantum field. Now, what we want to do with the quantum field is to compare two quantum states. We want to compare the vacuum state and a coherent state, specifically to quantify how distinguishable these two quantum states are and how that distinguishability depends on the mass of the field and on the dimensionality of the spacetime. Now, for this work and for this setup, and in order to be able to compute the relative entropy, we had to choose f to be compactly supported on the right Hindley wedge. So for anyone who might not be familiar, you can understand that Hindley wedge as follows. So you can draw a simple space-time diagram. Here it's for 1 + 1 dimensional flat space-time. And then you can draw a light cone emanating from the origin of that diagram. So it's these two diagonal lines. And as can be seen, it splits the space-time diagram in 4 regions. One that is above, one below, one to the left, and one to the right. The region on the right is what we call the right Hindley wedge, and the region to the left is what we call the left Hindley wedge. So we are choosing a test function that is compactly supported inside the right Hindley wedge. We might have chosen something on the left Hindley wedge as well. Nothing will change. So why we do that? Why choosing a compactly supported test function inside a wedge? We do that because we want to use the theorem by Bisogniano and Wichmann to compute the relative modular operator. It's thanks to this theorem that we are able to actually make computations. So essentially what it says is that the relative modular operator is basically the boost operator acting on the wedge region. So it becomes very simple to work with. Now, using the Bisogniano and Wichmann theorem, we can reduce the complicated expression to this very simple one, where the relative entropy is just the desmuted Pauli-Jordan distribution. Now we are at home, so it's much simpler to work with. And here we have this f prime appearing. So f prime is nothing but the derivative of the boosted test function at the boost parameter 0. And that's it. So this is what we have to compute in order to answer the initial question. Just as a small remark, this muted Pauli-Jordan distribution is nothing but the Pauli-Jordan distribution is muted against two test functions. And the distribution itself is just the imaginary part of the Whiteman function. So we have worked with the 1 + 1 dimensional, 1 + 2 dimensional, and 1 + 3 dimensional cases. These expressions for the Pauli Jordan distribution in these cases are well known. And I want to make a small remark here. In 1 + 3 dimensions, we have two terms, one that is supported on the light cone and one that is supported inside the light cone. Now, what I want to remark here is that if you look at the asymptotic behavior of the 1 + 1 dimensional Pauli Jordan, the 1 + 2 dimensional Pauli Jordan, and the bulk term of the 1 + 3 dimensional Pauli Jordan, what you will notice is that the asymptotic behavior for very large masses is very similar. So they are all oscillatory and differ by a phase and some constant factors in front of it. So if all these Pauli Jordan distributions are qualitatively similar for large masses, we expect that the relative entropy will be as well. Now we have to compute the smoothed Pauli Jordan distribution to obtain the relative entropy. And we have chosen this specific test function. Well, we could have made other choices, but this one worked nice with the numerics. And since we are dealing with multidimensional integrals, there is some sort of a challenge in choosing a test function that behaves well enough. So what we have here is a combination of bump functions. So in 1 + 3 dimensions, we have 4 bump functions, one for each space-time direction. And just for completeness, the bump function is given by this expression, and it is a smooth and compactly supported function. In 1 + 1 space-time dimensions, just to give some intuition, the test function, the concrete test function looks like that. This is our choice of test function. As you can see, it is a square-shaped test function. The region of support is square-shaped, and it decays from the center. So the center of the square is where the test function is, well, larger, and it decays towards the borders of the square. Now, we are using the parameters that you see on the right, alpha and beta, to be the same. So this is really a square. And in larger dimensions, it is a box with equal sides as well. So, and there is the distance between the center of the square or the boxes and the point where the wedges touch. We are setting this distance to be equal to 3 times the length of the square. We could vary this as well. Now, with this setup, we covered the following mass ranges. So we computed the relative entropy ranging from 10 to -10 up to 10 to -1 with logarithmic steps, and then we extended it from 10 to -1 up to 10 with linear steps. And now we have to deal with a lot of multidimensional integrals, and for that end, we relied on Monte Carlo integration, which seemed to be the best option to deal with this kind of situation. So for all of these terms, for the 1 + 1 dimensional Pauli Jordan, the 1 + 2 dimensional, and the bulk term of the 1 + 3 dimensional Pauli Jordan, we used 10 to the 8 sampling points to compute the integrals. And it took roughly 42 hours per batch of data. So to cover the whole mass range in each of these terms, it takes roughly 42 hours. When it comes to the light cone term of the 1 + 3 dimensional Pauli Jordan, we use 10 to the 9 points. We have been able to do that because the light cone term is mass independent, so it only had to be computed once, and it took an hour. So it takes more time to be computed, but the outcome is more precise. And since we didn't have to compute it for all masses, we done that with 10 to the 9 points to get a better precision. To make sure that the integration was converging and not actually just fluctuating randomly as we increased the number of sampling points, we compared our results with 10 to the 7, 10 to the 6, 10 to the 5, and 10 to the 4 points with the one with 10 to the 8 to make sure that the integrals were converging somewhere and not just randomly fluctuating. On top of that, the Monte Carlo integration randomly picks the sampling points, so it might happen that all sampling points are clustered in a corner of the integration region. To check that this clustering effect have not happened, we compared our results, our Monte Carlo results with the quasi-Monte Carlo results, because the quasi-Monte Carlo integration method is completely deterministic, so it don't suffer from this clustering effects. It is tailored for that. And now we arrived at our results. So on the left, we see the actual mass dependence of the Araki and Ullmann, or the Araki relative entropy, for different space-time dimensions. The red line on both plots is for the 1 plus 3 dimensional case, the green line on both plots for the 1 plus 2 dimensional case, and the blue dashed line is for the 1 plus 1 dimensional case. So as you can see on the left plot, in all cases, the relative entropy decays from a peak at low masses towards a local maximum that happens for intermediary masses. So what we see here is that the behavior of the relative entropy is not monotonic. And this was the main finding of this work, because upon a simple reasoning, we can infer, one might think that the relative entropy should decay monotonically, because as you increase the mass, the typical correlation range of the quantum fields becomes smaller. So one might argue, based on that it becomes more difficult to distinguish the two quantum states. And we see here that this is a half-truth, because there are mass regimes of intermediary masses where the distinguishability increases again and then decreases again. Now, on the right, we see a plot of the relative error in the integration. So from the right plot, we see that our results are reliable up to m alpha, up to masses of 7. For larger masses, the integrals becomes more difficult to compute, and we would need more sampling points to come up with better results using the Monte Carlo integration, and we could not afford to do that given our current time and hardware constraints. One more thing, these large frequency oscillations on the left plot are oscillations due to fluctuations in the Monte Carlo integration. They are not to be understood as physical manifestations of any kind of phenomena, at least not given the precision that we have in these integrals. And here is a close-up view of the region where the local maximum appears. And in this close-up view, we can also see the error bars for each of the cases. So as can be seen, even though we have an error bar that isn't so small, this error bar is not compatible with a monotonic behavior. So when it comes to the claim that the behavior of the relative entropy is not monotonic, we are fine within the error ranges of our computations. And what is nice is that the relative entropy, as we've seen, is completely given by this muted Pauli-Jordan distribution. And the Pauli-Jordan distribution depends only on the geometry. The geometry of the underlying space-time completely fixes that. So what we see here is a manifestation of how the geometry of the underlying space-time helps distinguishing two given quantum states for a free quantum scalar field. So the height of that local maximum is shaped by the geometry of the underlying spacetime, and this is kind of nice to see. And now I'll finish with my final remarks. So as I pointed, in contrast to the naive expectation that relative entropy would be monotonically decaying because of that, as we increase the mass, the typical correlation length becomes smaller, so one might argue that it's more difficult to distinguish two quantum states. So this is not always the case. There is also a clue that maybe for larger masses, the relative entropy will keep oscillating with decaying amplitude, but with an oscillatory behavior that is persistent. We are not able to verify that because we're not able to go to larger masses to actually see oscillations appearing. All this that we have seen is controlled by the geometry of the spacetime, which is what fixes the Pauli-Jordan distribution. So the questions that are left open are, well, for instance, what if we change the shape of the region of support of our test function? Or what if we change the length or the size of that square of the box where our test function is supported? So maybe something new appears, maybe not. What if we move our test function away from the wedge? What if we approach it from the wedge? So these things are still open to be explored. Additionally, one might wonder if we can go beyond wedge regions. For instance, maybe I would like to consider diamond-shaped regions. So what would happen in this case? Would this conclusion still hold there? Well, this is a question that's left open. And finally, do this pattern that we just verified still hold in interacting theories? This is also a question for future works. So this was my presentation, and we all from the group would like to thank you for your attention. So this is our photos. And now, I don't know if there is time or not, but I would be open to questions.
Thank you so much, João. That was a very nice talk, very nice summary as well of the whole relative entropy to Takasaki and how to actually see the results and explicit examples. This is very nice. I don't know if we have any questions from the Zoom audience, but if not, then let me ask you a quick question, hopefully. Hopefully it's going to be quick. So this is all nice. I'm going to say, though, that I'm not very sure why you were considering only compactly supported coherent states, because in principle you could just use the relative entropy formula to perhaps like consider states, say a coherent state or something like this, that is sourced by a Gaussian, like or something that makes the calculations a little bit nicer, maybe even that would allow the calculations to be done in closed form. So could you maybe elaborate a little bit on this?
Sure. Well, our choice was like that because we wanted to be, we wanted to follow the more rigorous route. And since we rely on the Bisoniano and Wichmann results, what we rigorously know is how the modular operator acts when we have a compactly supported test function on a wedge region. If we use, say, a Gaussian function, it isn't compactly supported on a wedge. So what the result will be that we will not be able to use the Bisoniano and Wichmann theorem, and in practice, we won't know how to compute the relative entropy. Now, of course, we can make some sort of approximation and say that we might use a very sharply peaked Gaussian. So we have a very small, we will be outside the Bisoniano-Wichmann theorem, but only for a small margin. But that was the reason, just for keeping the rigor.
No, that's fair. I mean, there's some upcoming work that I'm involved with too, with my master student, that basically is able to consider Gaussians to do an expansion within a finite region. So it's basically like you start compressing not only Gaussians but Hermite functions, so that like you can still compute everything in closed forms because you have a generating function from the Gaussian and all this, but you start like shrinking the support effectively of your Gaussian so that you get something that is effectively completely supported. So that might be useful for that, in the sense that if you have closed forms, then you don't have to worry about all of the annoying parts of numerical integration and all this. So let's keep in touch about this, but this is very, very nice. Thank you so much for the talk.
Sure, thank you for your appointment. It was it was a fine point that you raised.
No, I mean, we should definitely talk in the future. This is very nice. Thanks. Okay, cool. So let's thank João again. Zoom isn't very good at getting the claps, but the YouTube folks are getting at the very least my claps. Okay, cool. So thank you so much. And I guess that now we move to the next speaker, assuming that they are here. So Siddhant, are you here?
Hey, yeah, I'm here.
That's perfect. Okay, and sorry, how should I pronounce your name? Siddhant Midha?
Siddhant is fine.
Siddhant, okay. Siddhant, and your last name?
Midha.
Midha, okay. Siddhant Midha. Siddhant Midha, okay, good. Perfect. Do you want to start screen sharing so that we make sure that everything is working?
Can you see the full screen?
We can see exactly what you can see, I think, yes. So we can see the full screen.
Awesome.
We can even see the button on click to share. So I think we can see exactly what you can see. Okay, good.
Okay,
so the next speaker of today, we're a little bit behind schedule, but it's all good. The next speaker, oh, sorry, you should keep your...
Sorry about that.
Now we lost the screen share. Okay. No worries.
Okay, awesome. Should be back.
This is all good. So the next speaker today is Siddhant Midha, and he'll talk about quantum radiation metrology. So please, Siddhant, the floor is yours.
So hi everyone, thanks for having me. I'm going to tell you a little bit about what I like to call radiation metrology, or if you interpret it a little more, you can call it holographic metrology. I personally work on many body physics and quantum information. So, you guys are experts in many things that I'm not, but I just want to give you a flavor of
this result, which is, sort of in the setting of open quantum systems and metrology. So I'm going to try to take you through these things. But the motivation for all that I'm going to talk about is actually sort of very experimental in the sense that it's inspired by what quantum technologies can now give us. And the idea is somehow very simple. The generic setting of a lot of quantum technologies, revolve around, let's say, if we take the example of cavity QED, the generic setting is, I have some, quantum systems that I have, let's say, maybe in a cavity, in the sense of cavity QED, then, I have a bunch of atoms in a cavity and they're undergoing some interesting physics. What I have access to in a lot of these experiments is sort of this thing which I can call the continuous quantum radiation, where the idea is that these atoms, are emitting photons into the cavity, and I can very easily sort of monitor that photon information almost for free in many experiments. And then I can sort of, ask a very natural question, which is, what can I learn about the quantum state of the atoms, from this sort of continuously emitted radiation? So you can really think of the atomic state here from the experiment as some sort of a bulk, and it's emitting continuously a radiation in a temporal direction. And then you can ask, how much does this temporal radiation know about the state of the bulk? And that's sort of, our motivation going in. So, just to sort of make sure we're all on the same page, I'm going to maybe take it a little bit slow. I'm going to talk about this metrology problem in general. What do we expect? What do we know? Then I'm going to sort of come back to this continuous measurement problem. And then I'm going to tell you a little bit about maybe, if time remains, tensor networks and how they help us actually surprisingly solve this problem analytically, which are, of course, tensor networks are interesting in their own right. And then I'm going to sort of talk about consequences of what we learned from all of this. So, all right. So the mathematical setting of metrology is, fairly simple. So instead of learning everything I want about, big complicated quantum state, which is maybe unreasonable, I'm going to sort of ask that, okay, my bulk state encodes some parameter, let me call it theta. And then I want to ask, somehow, how can I learn about this parameter? So the idea is you have some theta embedded in some real space. You can think of this theta now embedding it into some quantum space of quantum states. So let's say density matrices. And then you can ask, then I make measurements on these. So if you can take 2 points, theta and theta prime, which are the star and the square here. And then you can ask, how far, do they actually move as I make these embeddings? So that's, mathematically somehow specifying the procedure of making measurements on quantum states. And what we can sort of do is we can define a distance between two parameters, theta and theta prime, as a sort of pullback from the distance on the quantum or the classical space. And my claim is that this distance and its properties are actually sort of important in fundamentally bounding how much you can learn about this parameter. So, this is a divergence. So this could be, for instance, the KL divergence that many people are familiar with. But, let's just sort of talk about this abstractly. I have some measure of distance. What I can do is, I can make a simple Taylor series expansion. And then, the first non-trivial term I can get, what you can show is the sort of Hessian, which I'm going to call an information matrix. My claim is that, this matrix, which encodes the curvature of, how you make this embedding, encode some sort of information theoretic properties. And morally, it's easy to see that it encodes some local information in the parameterized space because, if I change my parameters and this, the derivative is somehow really big, that means that a lot of information about the parameters is encoded in this embedding. And what you can then sort of do is you can apply this to a concrete distance, which is the Kullback-Leibler divergence. And then you can sort of, you get this quantity, which I'm going to define and call the classical information matrix, so the classical Fisher information matrix. And this is a sort of, really cornerstone of classical estimation theory. And it has a lot of nice properties, which I'm sort of going to dig into. But the moral point is, you sort of get this as a Hessian of some information theoretic quantity. And then we're going to see how this helps us. The intuition is that this sort of quantifies how much my embedding knows about the parameter theta that I want to learn. And it turns out, through a lot of work in the last 20 years, you can sort of take all of these ideas into the quantum world, and you can sort of talk about, let's say in the simplest case, I have some parameterized quantum states. So let's say psi encodes some parameter, and the natural distance to define on pure states is, just from the inner product. And then what you get, and you may have seen this as like the Fubini study metric or the quantum geometric tensor, depending on which field you exactly work in, but it's sort of all over the place. You get some sort of information matrix on the space of quantum states. And it looks a bit abstract at first, but there's some simple calculation that goes behind this. And it satisfies a lot of like nice information theoretic properties, which essentially sort of tell us that, there is a well-defined meaning to this Fisher information. Now, these properties are not super important for us, but we can sort of discuss what this means. For instance, if I apply to a really simple example where I, embed a parameter theta by, let's say, evolution with the Hamiltonian H, then what you can sort of show is that this quantity, this, seemingly complicated object is just a variance of the Hamiltonian in my state. So, if my state is somehow spread out through the spectrum of many body levels of this Hamiltonian, then, this variance can be high. That's the rough idea. And, please interrupt me if there are any questions because, I can't see anyone's faces. But so these things are important because what you can now show, you can return to this original problem of how much can I learn about this parameter, and you can show bounds on this estimation process with these quantities. So the setting is as follows. I have some quantum state, and I have some, dynamics which encodes a parameter onto that state, and then I make measurements. And then I ask, how much can I learn about this parameter theta from these measurements? And what you can show is that, there's a sequence of nice inequalities, which essentially show that the best you can do, so the best error you can get is actually lower bounded by how much this Fisher information is. So the error in the best case scale is as inverse of the Fisher information. So really, if your Fisher information is really bad, this lower bound is telling you that you can never build a good protocol to learn about what's going on in the state. So, a sort of growing Fisher information is really a necessary condition for, learning about such quantum states. And, we can sort of, get into details and sort of characterize how that growth rate should look like. And that's really the, what modern metrology sort of focuses on. And the I and the F here are the classical and the quantum Fisher information respectively. So the idea is that the quantum Fisher information bounds everything that you can do, irrespective of whatever measurement you can make. And, any measurement that you make will fix a classical Fisher information, which is the actual statistics that you will see. And, it's not so hard to show that there exists some, optimal measurement. So if you're familiar with a little bit of quantum information, there exists some positive valued measurement operators such that you can use those and you will actually, attain the quantum Fisher information. So it's a well-defined attainable quantity in that sense. All right. Now, we can ask why, there's like a philosophical question of, all of this should hold true in the classical world itself. So why do we need quantum mechanics here? So what can quantum mechanics sort of offer us? And then consider the following experiments. I repeat the same system that I had the last time, let's say n number of times. And, I have the same dynamics that I want to learn about, which is generated by some Hermitian generator. You can think of it as a Hamiltonian H. What you can, again, very simply show is that the Fisher information of this experiment is just a variance of H. And by the properties of the Fisher information and Kramer-Rao bound, what you essentially have is this inequality, which, should look familiar. It's saying that the variance of the parameter that you can learn is lower bounded by inverse variance of the generator. And if you think about this is just a Heisenberg principle. So really, this is a very fundamental statement, and, we should not be surprised that this holds. But, you can ask the question, okay, can I actually attain it? So what is somehow the state that I should, start with? So to actually attain this maximal Fisher information. So if you have a Hamiltonian with two levels, you can just start in a state which is uniformly spread out over those two levels, because that is the sort of, maximal variance state. So you can just start in this product state and you will actually attain the ideal Fisher information. And you can make a simple measurement, sort of measure in the conjugate basis. And what you get is that the error in this experiment scales as 1 over n, where n is the number of probes I had. And this is colloquially in this literature called the standard quantum limit. So the idea is that you have some n unentangled probes, and then you sort of run this experiment, and the best you can do, your sensitivity variance scales as 1 over n. But really, we do have quantum mechanics, so we can do more. So I can do the same experiment, except I can start from a collective state, so some entangled state over these n probes, and I can make some, more complicated measurements, and I can ask, can I do better than that? And indeed, you can. So what you can show is that for the same sort of setting, if you have a GHZ type state, so for instance, which has a macroscopic superposition over all the, up and the down levels, and this is of course entangled, this will, and you perform similar sort of measurements as you did before, what you can actually precisely show is that you will get a sensitivity which actually scales as 1 over n squared. So as you increase the number of probes, you will get more and more sensitive in the parameter that you want to estimate. And so this object scales as the square of the number of probes, and this is colloquially called the Heisenberg limit in quantum metrology. And the idea is you can actually for this setting prove that this is the best you can do. So this is the best you can do for measuring the setting, and we have a simple protocol which actually achieves this. So really many questions in quantum metrology in the abstract sense are really, can you achieve this square advantage or not? And the philosophical sort of idea is that that's really quantum mechanics helping you out. So, the takeaway is that Heisenberg limit is n squared and the standard limit is n. And then we want to understand when this is possible. All right. So coming back to the sort of setting that we want to answer, which is the idea of continuously monitored systems. So as I said, there's a very nice cavity QED motivation, but as it turns out, this turns out to be just really a really nice sort of problem in many body physics and quantum information in general, and it's tells you about a lot of things. So the idea is, my experiment is somehow giving me these time traces which look crazy random, but can actually do some processing on them to actually learn about the state of these atoms or the bulk, if you may. So right, so let's try to sort of model this process in generality. So you can think of these temporal radiation modes as small d-dimensional systems. So at each time you have a new radiation mode coming in. Now the idea is that you have a bulk, which is the state psi, and there's some fixed interaction between the radiation mode and the bulk. And at each point, a new mode comes in, it interacts with my state, and then goes out. And then the idea is that the radiation that has gone out is essentially entangled with my bulk state, and then maybe contains information about what was going on in that state. And then you can ask, okay, I make a measurement on tau of these radiation modes. My naive, intuition from quantum metrology tells me that, hey, maybe it's possible to achieve like a tau square sensitivity in the number of modes. And that's one question you can ask. The other question you can ask is, maybe my bulk was made out of n atoms or n particles. Can I achieve an n square factor as well? So that's the sort of things we're going to try to answer. And mathematically, this is fairly straightforward to model. You can sort of show this as a superposition over all the possible trajectories of the bulk and the radiation that you can get. And you can also sort of take an open quantum systems point of view on this and ask, how do I model just the state of the bulk? And that can be modeled by what we call a Lindblad generator. And this is the idea of, I can have sort of a Markovian generator that models the dynamics of my bulk. So there's really two complementary perspectives on this. And so we have these capital D, which is 2 to the n. So I have n particles in my bulk. And, I ask, in these experiments, the idea is I cannot measure the bulk. So I can only measure my boundary state. So I need to ask, how much can I learn about the bulk by only measuring the boundary? And how does that scale in terms of this number n and the number of boundary modes that I measure tau? So those are really the motivating questions going in. And let me also mention, when our paper came out, there's in the similar week, in the same or maybe the next 2 weeks, there was many interesting related papers answering different sort of questions in the same field, and you should also check them out. And so, the tool that we're going to use here is we're going to map this problem into a very nicely studied object in many body physics, which are tensor networks, or more specifically, matrix product states. The idea is that I can take this, this entire sort of process that I defined to you, and I can just write this down as a tensor network. where the idea is that this red wire encodes the state of my bulk, and these black wires are the state of my temporal modes. So at each point, I have a new temporal mode coming in. I have some big tensor. Now a tensor here is just a multi-dimensional array, which we sort of know how to deal with. And I have this unitary dynamics, which sort of takes in at each time the state of the bulk and a state of a new boundary radiation mode and emits the boundary radiation mode out into, let's say, the experiment. And the idea is I can only measure the boundary radiation. Right. So, and what we're going to do is we can sort of if you look at this problem and if you sort of think about it, this is exactly the setting of a matrix product state, which has been known by work such as Sean et al. Since 2005. So the idea is you can map any problem in D plus 1D dynamics onto such a tensor network, and this can also hold in, let's say, 1 plus 1D dynamics. But here I'm thinking of a 0-dimensional bulk plus 1D temporal radiation. So we know a lot about these matrix product states, and let me just give you a primer on them real quick. The idea is that in many body physics, I want to think about how to represent this big complicated exponential sized object, which is my wave function. So you can think of this as a tensor, where if you have L particles, I have L legs sticking out. This might look kind of complicated, but the idea is I just specify a number on these L legs, and I just get the amplitude of the wave function. But we know that there are many states which satisfy such like an area law of entanglement. So they don't actually need such exponential complexity to be able to describe them. So what you can sort of do is a very simple mathematical trick of doing a singular value decomposition. So the thing with these tensors, why they're nice, is that you can just think of reshaping this object into a matrix. So you grab one of those legs and take it to the left, grab the rest L-1 legs and take it to the right, and do a singular value decomposition. Think of this as a matrix. And then what that actually gets you is essentially the Schmidt coefficients on that bipartition. And you can sort of keep doing this again and again. And the idea is that, if entanglement in this state was controlled to begin with, then these coefficients are actually going to be super efficient to describe. So you really get, a representation of the state which mimics the entanglement pattern that, you had in that state, which is really nice. And then, the idea is that you can represent each of these local objects as small tensors. So this is, again, just an array with multiple indices. And chi here is sort of called the bond dimension of this tensor. And these are proven to sort of represent efficiently the ground states of 1D local gapped Hamiltonians and, much more states. The idea is that by definition, they satisfy an area law of entanglement, which is controlled by this bond dimension. And, from a complexity point of view, they encode much less parameters than the big Hilbert space. And the idea is that as you grow this sort of tunable parameter, which is the bond dimension, my ansatz of MPS will sort of consume the whole Hilbert space, as you keep growing this. But within this ansatz, I can sort of make efficient computation. And for us, this problem is going to simplify quite a bit because we are considering dynamics, which is time translation invariant. So it's Markovian. So this is going to look like a matrix product state, which is somehow homogeneous. And, any physicist knows that if you give you a sort of homogeneous problem in 1D, the first thing to do is try to write down a transfer matrix approach. And that's exactly what you can do for a matrix product state. And the idea is you can sort of, squish these, the bra and ket side together to write down this matrix. And, believe me, if this looks strange, but the idea is that this matrix tells you a lot about the correlations on this state. And if you can sort of show that this matrix is gapped, then you sort of have a finite correlation length in this on the spins. So for us, our spins are essentially the boundary radiation modes. So I'm going to denote a correlation length by this parameter tau star, because really we should be thinking of it as time. But the idea is that this technology really helps us, think about the metrology problem in full generality. Right. So with this, we sort of state the main, result. It turns out you can sort of, just take this big complicated metrology problem, which is specified either by Lindlardian or the unitary that it's composed of, and you can sort of write down this entire solution of what we wanted to know as just a bunch of tensor network contraction, which look maybe very strange if you haven't seen this before, but trust me, like this is fairly simple. And this doesn't give you a lot of intuition, but the idea is that I can just use this MPS mapping to write down an essentially exact answer to the Fisher information that I was concerned with. So the Fisher information of the total state, which is the bulk as well as the boundary, which for technical reasons, this is the first thing we get. So I get the Fisher information of the bulk and the boundary, which is exactly this. Now, this formula naively, it looks kind of strange, but we can sort of analyze it further. But before we proceed, the idea is that, the Fisher information of the bulk plus boundary is not super helpful, because we started with the premise that, I can't measure the bulk, I can only measure the boundary. So, and it, turns out that these techniques actually let you do that. Before we go there, though, I would like to mention that this problem has been studied, since in a sort of Lindblad setting since 2014, and there have been very nice papers writing down sort of also exact answers to this. Those formulas have been a little bit, I think, opaque in the sense that it's hard to sort of show the general picture with them, but you can make sort of efficient predictions. So those are also super valuable in thinking about this problem. But Oh, okay. Yep, sounds good. So, the first thing we can do when you map this to this tensor network picture is that we can sort of directly use a lot of ideas from quantum information. And what we can actually just show is that, it's actually fine that the bulk cannot be measured. So we can actually get away by just measuring the boundary. So the idea is we can actually formally trace out the bulk and then look at only the density matrix of the boundary. And you can rigorously prove is that the boundary only or the radiation only Fisher information is sort of lower than the the total Fisher information by only some constant in time. So you will sort of incur some, loss as you sort of throw out the boundary state because you can't access it as the observer, but that loss is some, bounded by the correlation length of the system. So really, you can actually get away by just measuring the boundary. And the proof idea is a sort of simple, but maybe strange if you haven't seen this before. But in quantum information, it's sort of called decoupling, and the similar ideas can be used to prove this. So this really correlation length is going to be crucial for our sort of picture. So we can now come back to the question. I had, number of boundary modes T, number of, bulk atoms N, and then I can ask, how does the scaling look like in both of those? And, where did, Heisenberg go? And then what you can show is that generically, you actually cannot get superlinear scaling in the number of boundary modes, because generically, you can sort of define this you can define the word generic in a very strong way, but I'm not going to get into it here. But the idea is that eventually you will get something which is linear in the number of boundary modes because of a finite correlation length. But you're going to get two parameters which control the density of the Fisher information. The first parameter is going to be something very interesting. It's going to tell you that it's related to the variance of the steady state of only the bulk in the Hamiltonian that you sort of wanted to measure. And this, in fact, can scale with the number of atoms squared. So this you can really get Heisenberg limit here. And the second object is somehow more complicated, but you can show it morally scales linearly in the correlation length. So the correlation length is really important in the sort of asymptotic expression that you get for the Fisher information. But the main idea here is that you can provably, without ever measuring the bulk, recover sort of Heisenberg scaling in the number of bulk atoms, which is really somehow, magical. But, this is provably possible. And the steady state picture is interesting if you think about open quantum systems. But the general picture is that, if I look at this bulk Fisher information as a function of number of, boundary modes, boundary Fisher information as the number of boundary modes, it will scale, as best as it can in both the bulk atoms and the number of boundary modes, so n squared, t squared, for up to a time which is roughly the correlation length of that MPS we talked about. And then eventually it can scale still in Heisenberg scaling in the number of bulk modes. However, you will get linear scaling in the number of boundary modes. And this correlation length is going to be crucial here. So I should just, try to wrap up. But the idea is, you can actually sort of write down very interesting systems and try to study this in much more detail, also do numerics. So the idea is if you now make your bulk sort of situated at a dissipative phase transition, so you will have sort of a gap which goes down with system size, which will sort of imply that your correlation length increases with system size. And this is inspired from what we call some of these time crystal models. But the idea is that you can actually get somehow, very nice, even n cubed scaling in the final Fisher information, because if your correlation length also scales with n, and then if you have an n squared because of the variance and combined, that looks like an n cubed, which was really surprising to us, but you can actually sort of, through this analysis, prove why that should be the case. But let me just, summarize. So we discussed the overall problem of quantum sensing, which is, of course, interesting in its own right, but we specialize to the idea of continuous monitoring. So we have this, bulk state that you cannot measure, emitting boundary radiation interpretation, and then we can ask how much can we learn from the boundary radiation about the bulk. And we sort of realized that, tensor networks form a very nice analytical as well, of course, numerical tool here. And we sort of, can recover a notion of Heisenberg scaling in these settings, which are, of course, related to open quantum systems. And many questions remains. So because, I have sort of shown that the Fisher information is interesting, but the idea is that what sort of measurements do you actually need to do to attain that Fisher information? I have actually not said anything about that. And in general, that's sort of an open problem. In general, it's hard to show when can you actually do it with local measurements, which are of low complexity. And in general, can you sort of, what is the complexity of this sort of bulk reconstruction, if I may use those words, in such settings is, I think, in general, still open. And with that, let me thank my collaborator, who's also my advisor, Sarangon, for the collaboration on this project. And, you can check out the paper or talk offline if you're interested further. Thanks.
Thank you so much, Siddhant. That was a very, very nice talk with a very nice summary of quantum sensing. I think that honestly one of the best ones I've ever seen, like the whole idea and the quantum Fisher information. So thank you very much for that. Unfortunately, we are a little bit over time at this stage. If someone in the audience has a very quick question, then we can do that. But if not, I would suggest that we move to the next speaker. Boyu, are you Boyu Gao? Are you here? Yes. So let's think then again. Okay, great. So now we have the last talk of the day. The last talk of the whole RQI circuit, as a matter of fact. So, do you want to start screen sharing so that we can? Yeah.
Can you see my screen?
Yes. Perfect. We can see everything you can see and the cursor. So this means that you can point at things and all that. So thank you so much for applying for this. That's the kind of line of work that Natalie has been conducting in her group has really inspired much of my work and the work of many others in the community. Okay. And it's great to have people from that side really joining in a little bit more in the community and presenting the work. So that's very nice. So okay, let me introduce Boyu Gao, who is the last speaker of the RQI circuit, and he'll be talking about detecting and preparing space-like vacuum entanglement. So please, Boyu, the floor is yours.
Okay, thank you for having me. And today I will be basically summarizing 3 of our past works in this talk, all under the topic of detecting and preparing space-like vacuum entanglement. And first, I want to do a little motivation of why we care about space-like vacuum entanglement. Of course, the first reason will be that it's very interesting to study the quantum, which is in case, but the two-point function actually encode both quantum and classical informations in the field. So we want to find a way essentially to isolate the quantum correlation part out. And the model or the method we'll be using throughout this series of works is that we first put the field on a lattice and we ask what is the entanglement between the disjoint regions. of the field. And we first pull out these discrete regions, which is essentially a mixed state, and we quantify this mixed state through logarithmic negativity, which is just quantifying, for example, logarithmic negativity can quantify mixed state entanglement in terms of you do a partial transpositions on one of the regions. Like you have AB, you have two different regions, and you do a partial transposition on one of the regions, and logarithmic negativity just shows how unphysical your state is. And this level of unphysicality give you ideas of how entanglement this mixed state is, and how entangled this mixed state is. And in our field regime, because it is really a continuous variable, it's really continuous variable here, and it's the logarithmic negativity kind of manifests as a local P minus P transformation. And it is also the reason why, another reason that is good for field application is because the log negativity is a UV finite quantity. In other words, if you take the continuous limit of your lattice, you will see many quantities that will diverge. For example, the single region entropy will diverge, but the log negativity is a quantity that will converge in the continuum. And importantly, recently shown that log negativity is a necessary and sufficient entanglement measure in the scalar field vacuum, which is pretty rare for you to have a necessary sufficient measure for mixed state entanglement. Here is an example essentially for how log negativity scales as a function of the separation ratio, where we have the separation ratio is defined by the distance between the disjoint regions and the width of the disjoint regions. And all these different colors are indications of a trajectory towards the continuous limit. And you can see that as the continuous limit is approaching, all these different curves actually approaches to an exponentially decaying scaling. This plot is for the massless field, where the negativity decays exponentially, which is exponentially faster than the two-point function, which only decays polynomially or logarithmically. So that is also an important feature of negativity or quantum correlation in the field, is that it decays exponentially faster, essentially, compared with the two-point correlation functions. And also, a very interesting feature of this plot is that this plot actually shows the quantum correlation is presented at all distances in the field vacuum. But there are in the literature, people have actually shown that the accessible entanglement in the field vacuum, actually there's no entanglement that can be accessed beyond the level of Compton wavelengths. However, we really have the negativity presented at all distance in the field vacuum. This seems kind of a little contradict to what literature says. So this is actually a motivation of why we are starting this line of research. And this is actually also the first question that will be answered. So by accessing entanglement, we'll be kind of simplify this concept. Like we are using the single mode detector as kind of depicted here, and we access the entanglement of this disjoint region mixed state, right? And if we quantify or we depict pictorially, like we depict the quantum correlation between the mixed state as all these kind of pretty chaos-like lines, and we want to ask, how can we actually access the quantum correlations in the sea of this chaos? The answer is that you want to really know where this quantum correlation is embedded. And to know where this quantum correlation is embedded, it's better off that we will understand the entanglement structure of the disjoint regions. So another thing that negativity is perfect on is that the negativity provides us a negativity subspace, where we can analyze the entanglement structure in that subspace. And after analyzing this subspace, we find that there's some really nice orthogonality properties, and you can design the local unitary gates or local unitary transformations through this property, and then you can really have the pairwise entanglement after applying this unitary. This pairwise quantum correlation or entanglement actually tells you what is the optimal interaction or what is the optimal interaction your detector can have with the local field region, so such that you actually extract the maximum amount of quantum correlation. The optimal detection profiles thus looks as follows. The two very interesting features that this optimal profile is through accessing directly with these through the guide of these transformation properties we discovered is that this profile actually oscillates. As you see, when the quantum correlation becomes smaller and smaller, you'll see that this profile becomes more and more complex and oscillating. And another very interesting feature of these plots is that the interaction profile, by interaction, I mean that this single mode detector will have some will kind of interact with the field space such that the entanglement can be extracted from this interaction. And it will interact not through these field space and the local conjugate field space. The very interesting feature that you can see in this plot is that the field space and conjugate field space interaction profile is actually different. And this actually answers a very interesting question I just posted on the last slides, is that the reason why previous work doesn't detect entanglement beyond the competent wavelength scale is that they have assumed that the field space and conjugate field space interaction profiles are the same. And they did an optimization actually with these assumptions, and this actually forbids us from seeing entanglement, access entanglement beyond competent wavelength scale. But through this entanglement structure analysis, we can really just obtain the optimal detection profiles through, and this optimal detection profile actually tells us we shouldn't assume that the interaction profile in the field and conjugate field space to be the same. And now, after kind of figuring out that the entanglement can be accessed at all distances, another question to ask is that how can we access space like pure vacuum entanglement? It's because this is also an important topic, is because the pure state entanglement is actually what we will be leveraging to do some informational protocols and to do quantum simulation, right? So that to access pure space vacuum entanglement, we'll be designing a measurement and classical communication protocols such that we are measuring the volume, and then we kind of tell the observer in the AB region what we measure, and so that the observer in the AB region can do local unitaries to with this feedback information from the C to actually purify these truant mixed states. Where in our recent work, we actually design a protocol that allows any measurement to be conducted in the region C, and we also establish a connection between any measurement to conduct it and any noise to extract it from the AB region. In other words, we don't really need to focus on the C space in order to analyze the maximum and minimum pure space like vacuum entanglement in AB. What we can do is that we can really just focus on the noise model of the region A and B, and to obtain a maximum entangled pure state or minimum entangled pure state, and run through our protocol, and to obtain what the measurement profile will be in the C space, such that the resulting A and B space pure state is the one you want. And after establishing that, I will say that our task becomes a little simpler, so such that we can only just focus on the noise model in AB and don't need to worry about that much more complex measurement profiles in C, right? And here is a plot that in the past work has Natalie has done, that she did local measurement in C space only, and she didn't at that time do a global measurement in C space, but just do local field and conjugate field measurement in C space. And she found that the resulting pure space-like entanglement scales with the 2-point functions. And now through this protocol that we designed, we can really ask, is there something that scaling that better than what previous work has found? And the noise model we'll be using is the Gaussian classical mixing channel noise model, where we'll be manipulating on the level of covariance matrix. And in this work, we actually take one step further to identify a double cone geometry inside of this Gaussian classical mixing noise channel, and we identify ways to maximize and minimize this double cone geometry, such that we are obtaining a approximation of maximum or minimum pure space-like entanglement. And note that any of these noise subtraction again can be identified, or we can find a unitary over here to measure, such that we are achieving our goals for the maximum minimum pure state entanglement. And by running our algorithm, we kind of immediately show that there exists a scaling that is exponentially slower than 2-point functions, and it provides a lower bound to the maximum pure space vacuum entanglement we can get, which is at this part the maximization of this double cone geometry. We have derived it analytically, and and show that this is actually exponentially slower than the previous results. And now we actually, what I have just shown is a normal scale plot. Now that we turn it to a log scale plot, right? And we ask ourselves, what's the minimum pure space entanglement we can get? And this minimum pure space entanglement is actually also connected to the entanglement formation, where you spend minimum entanglement to prepare a mixed state. And for the two-mode state, this minimization is actually easy to find, because for a two-mode state, the geometry is just a 3D geometry, and we can essentially do a one-parameter searching, right, in this two-mode parameter space. But for the multi-mode geometry, as what I've just shown here, thanks to this double cone modeling that we came up, we are able to do this multi-mode optimization through the semi-definite programming, and where this quantifier of the double cone distance actually provides a necessary and sufficient measure for entanglement or solvability. And by conducting this semi-definite programming, we are able to identify the pure state scaling exponentially, like following the curve, the black curve of the log negativity. And this actually provides an exponentially faster improvement of a previous work, where the previous work, recall that it only kind of measures locally in the field space or conjugate field space. So note also, like, what we have been doing is all like measuring globally in the C space. We are doing a global measurement, and this provides a exponentially faster or exponentially slower bound on the GOA and GOF, all due to this global measurement that we conducted in C space, where we have where this probably could, due to some break of these genuine multimode scalar field correlations, and it actually being reappear through our protocol in the disjoint regions, such that it kind of dramatically increase or decrease this pure space like vacuum entanglement compared with only measuring locally. As a summary, what we have learned right here is that the quantum correlations in the field vacuum scaling is actually doesn't following the 2-point functions. It's actually exponentially faster than the 2-point functions. And also the mixed state entanglement, because our disjoint region state is a mixed state. The entanglement of the disjoint region is actually not a single number. It's actually operational related. So that entanglement is essentially also a operationally related quantity, especially mixed state entanglement. And the second is that understanding quantum correlation leads to new applications. For example, the profile derivations, the detection profile derivation actually rely a lot on these entanglement classes we have been identified, i.e. these unitaries we actually applied to the disjoint regions. The unitary is essentially a manifestation of that scalar field is actually sit in the unsolved entanglement class. So understanding entanglement can really help designing this interaction profile, which is something we can achieve in a lab, for example. Right? So understanding quantum correlation leads to new applications like detecting and preparing space-time vacuum entanglement, like quantum simulation, etc. And speaking of the quantum correlation, all this entanglement structure that we found in this talk, actually also we found it in this ion trap quantum computer, where you can see this top plot where the dark lines are for the scalar field and the bright colors are for this entanglement distribution in this ion trap ion chain. And these entanglement classes also presented in the the ion chain local axial motional modes, so that it could open much possibilities of, for example, future quantum computing. And lastly, I want to emphasize that this series of work actually manifests that it is possible for us to will quantum fields differently. For example, as a quantum computational resource. Here is actually a diagram of how our model, how our measurement noise subtraction protocol is based on, where you can see there's something that there's something that we want to perform, and we have identified an algorithm to calculate that step by step. And as a result, if we want to do an entanglement harvesting, or we want to extract maximum pure space-time entanglement from quantum fields, what we can really do is to run our protocol to extract the maximum pure state entanglement, which actually decays exponentially slower than these 2-point functions. And there are definitely more, right? Our series of work actually is just a starting point of studying this very interesting and nice entanglement distribution in a vacuum. But there are a lot of room for this beyond what I have listed here. And that's pretty much it for my talk. And thank you for listening.
Thank you so much, Boyu Gao. This was a very, very nice talk. I think that this topic is very interesting for many people in the community. And so you're a PhD student working with Natalie right now, is that it?
Yes.
Okay, great. And when do you graduate?
This year.
Okay, good.
Actually, next year. So I will be looking for jobs this year.
No, I mean, I've been following the work you guys have, and it's really very, very nice. So let me open the floor for questions from the audience. And if there are none, because, well, this is the last talk and very few people have been provided with the Zoom link, let me ask you then a couple questions, because again, this is the kind of thing that interests me a lot. So you have these kind of like oscillatory exponentially decaying behavior for the negativity, right? Like you can see this, for instance, in this plot right there, but also in previous plots, right? It's like it just doesn't go down exponentially. It oscillates a little bit when you're asking questions about negativity between two regions. So this is if I understand correctly, all of the results you have are for lattice simulation. So you have a lattice and you have this interacting lattice of harmonic oscillators, and then the argument is that as the lattice separation goes to zero, then you reproduce a field, right? So because these oscillations there, it's there's there's a recent paper by Robert Johnson and Jason Pye and a student that basically in 1+1 dimensions they were able to find analytical expressions for the most entangled modes, or for the negativity cores, if you will, between two intervals. So given two intervals, they can find this mirroring corresponding to they solve the eigenvalue equation for the negativity, if you will, analytically, right? And they don't find any kind of. It's super cool. Like if you want, I can send you I think that paper should be shared. It's like it's a very, very nice paper, very nice study, and the techniques they use is also super cool. But definitely, you guys should take a look at this. But what they find there is that, well, there's no oscillation there. What they find is that then it's just really like it's exponentially decaying, and once you're getting close to separation equal to zero, then the negativity kind of diverges, like as expected, right? But but there's no oscillation there.
The negativity shouldn't diverge because from our experience, negativity is UV finite quantity, so it should come.
No. It does diverge when the regions have a point of overlap, and that is because that is the limit that they can take. But in the lattice, you always have to have a finite separation that is hard to But it's but with no cutoff, like what they find in 1+1 is that it does diverge as you bring the R tilde to zero in your picture there. With no lattice.
But for non-zero R tilde, it shouldn't diverge.
No, of course, no, it's finite. Yeah, it's finite, and they have the closed form expressions for all. It's very nice. It's a very nice work.
Yeah, definitely.
But interestingly, they don't see these oscillations, right? So I wonder whether, because again, everything that you're doing is always using these lattice simulations with harmonic oscillators at each point interacting. So up to which extent can we trust that the results you have are going to hold in the limit where you're actually talking about a relativistic quantum field theory as opposed to just talking about a lattice of harmonic oscillators? And again, I gave you this example of the negativity just being exponentially decaying with no oscillation in their case, but just to try to understand what are the discrepancies we should expect to find.
Yes, these oscillations is also very interesting behavior we have aware of. These oscillations are lattice artifacts. So that's a new lattice artifact that we haven't found an explanation of why this artifact exists. For example, as you look at this plot over here, you can find there's a bunch of lattice artifact presented in this plot. Like for example, this point. The negativity shouldn't disappear, but on the lattice it disappears. And if you take the continuum, negativity is back. So that this lattice artifact Natalie managed to explain it pretty well by proposing some a concept called the UV-IR connection. But these oscillations is yet another lattice artifact that we haven't found the reason why that's the case. So, and I would say that's a very interesting lattice artifact.
Okay, good. Thank you. Amazing. So I guess I mean, I'll invite you to stay a little bit in the Zoom talk, so that in the Zoom call, so that we can share you the references and all this. Before this, let's thank you again, and again, this is amazing work. Congratulations for all of this.
Thank you for having me.
Would you mind stop sharing your screen real quick? Let me just wrap up the circuit then, and then we can go from there. All right, so I guess that this is the end of the RQI circuit. We started in the end of May this year, and every single week, every single Friday, we've been having talks, we've been having everything, and it was an amazing experience to see what different institutions have been doing around the world and all of these things. And it's really amazing research, and it's amazing people doing this research. Now it was also very good to have the people from smaller institutions or from places that didn't apply to really get to also share their work and all this. So well, with this, thank you all for tuning into the RQI circuit, either online or in person, or for helping organize and all these things. It's been a pleasure to do this, and hopefully someone else will take this job in the future. Maybe I could be willing to do something like this in the future, but regardless, it's been a pleasure. And well, thank you all for watching. Thank you all for tuning into everything. And it's very, very good to see how RQI research has grown over the past years. And I think we're making progress on so many fronts that it's good. It's really good to have this. So thank you so much for watching, and I'll see you whenever the next RQI circuit happens, or the next RQI North, or the next RQI event. So thank you so much for watching again.